function in terms of the Adler function have the following form. And in this equation, the integration contour lies in the region of the analyticity of things.
Been doing with younger collaborators in the last years, and you have all the details here. The first thing we did a few years ago was to extract alpha S from the hadronic W decays at NNLO at the time. And more recently, last year, we updated this study of extractions of alpha S from W decays at N3LO. And also, we reanalyzed the Z boson data, as you will see, because there were changes that were not included, that are not included in the PDG today, and we improved that too. So I'm going to speak about these state-of-the-art extractions of the QCD coupling from electroweak boson decays at N3LO. So we've seen this various times during the week. As you all know, we determine alpha S today from the combination of 7 experimental observables. And if you look into details, half of them basically are derived from E plus, E minus data. And even more so will be in the future, as you will see. So W decays, as you will see today, are not competitive in terms of alpha S extraction, but they will be in the future with high luminosity plus or minus machine at the W threshold. And then, of course, we will also have E plus E minus going to TT bar also in any future circular or linear collider. So voila. So what is the current status of, because right now, the only thing we have, if you check in the PDG, is this extraction from hadronic CDKs down there, the Z pole. And what is the current status? So let me tell you, if you open the PDG today and you check what alpha S gives you, you will see that there are these two extractions discussed. First one is fitting 3 Z boson pseudo observables that had been measured at LEP and SLC. Basically, the total width of the Z boson, which is known to within 1 per mil, and then the ratio of hadronic to leptonic widths, the cross section at the peak, hadronic cross section at the peak, and so on. So all these things are known at N3LO today, and by comparing the experimental data for these observables to the N3LO calculations, one can derive, and this is done in the electroweak section of the PDG, one can derive alpha S with 2.3% uncertainty. And that's a value that is carried forward into the QCD section, together with a very similar extraction, which is now what the GFITER team did now, is to basically leave the alpha S MZ parameter free in the global electroweak fit, and then just use all data to try to extract alpha S, and you get something similar, 0.1194 with 2.4% uncertainty. So that is the current situation. These results are very similar because the data, the full electroweak fit, is basically the data that has more weight is the same 3 Z peak pseudo observables here. So that's why you get basically the same result. Now, what about the W boson? That's something we did a few years ago, and I reported this in our last alpha S workshop, but you will see the improvements that we've done more recently. So the width of the W boson is known at N3LO. And again, as for the C boson, the sensitivity to alpha S does not come from the Born level. The Born decay width is purely electroweak. So it comes only through higher order corrections. You see them here, and so on. So and mix electroweak plus QCD corrections. And you see here that for this is true also for the total width of, for the hadronic width of the Z boson. Basically, the pure electroweak decay, this diagram, accounts for 96-97% of the total width, and then you have corrections of the order of 4% in that are brought in by higher order QCD and electroweak corrections. Okay, and those are the ones that are sensitive to alpha S. That's why even with a measurement of the width of the Z boson to within 1 per mil, you can only derive alpha S to within 2%. because of course you are not, I mean, the most of the width is pure electroweak, and the corrections are only 4% of this. What we did at the time is to try to do the same analysis done for the Z boson to the W boson. So and propagate all the uncertainties properly. So what we compute the partial decay widths and the QCD ones, the electroweak and the mixed ones, and we determined this, and we did a fit of the ratio of hadronic to you have it here. Of the branching ratio, hadronic branching ratio, also we did the ratio of hadronic to leptonic, but this is identical. You get an extraction of alpha S of 0.117 plus minus 0.042. And mind that this is not a 0.042. This is not a 4% uncertainty. This is a 40% uncertainty. Well, actually, it's 35% uncertainty. And this is mostly because of two reasons. First of all, we have a very large parametric uncertainty coming from this from CKM sum of a square elements. BCS here is known to within 2%, so this really introduces a large uncertainty in the Born cross section, which is completely insensitive to alpha S. So that's what that brings this huge uncertainty into the alpha S derive. And then also the experimental data, we only have 50,000 W hadronic boson decays at lab time. So this also brings in a large experimental uncertainty. So that's something we did back in a few years ago. Sorry. What we did more recently is to include some new developments, both for the Z boson and for the W boson. Let me explain to you. Let me explain to you what we did. First of all, this team, Dubovich, Chen, Freitas et al., in two papers, they computed first alpha, so this is electroweak corrections, alpha square and alpha cube electroweak corrections to the Z boson pseudo observables. And so these terms here now, and now they include alpha 2 and alpha 3 corrections that were not that are not in the PDG. So this analysis here have only alpha corrections and mix QCD and electroweak, but not the higher order pure electroweak. And those induce, of course, a small uncertainty. Sorry, those are very small corrections, but still, if we are aiming to precise, then we have to a precise extraction. As you will see, we need to start worrying about this. So we assess now the impact of these corrections and the corresponding theoretical uncertainties on these seed observables. Today they are at the 0.01% for the Z and 0.02 for the W. This is the pure uncertainties from missing higher order corrections. I will come back to this later on. And also we determine the parametric uncertainties, which are very small, 0.03 for the Z. Mostly now this is okay. This is driven by alpha S now and MZ, but of course alpha S we want to determine. So it is not an uncertainty when we derive alpha S from this. It is not an uncertainty anymore. It should not be considered uncertainty. This is the parametric uncertainty of these seed observables. Okay. For the W boson, the parametric uncertainty is 1.7. Again, because of VCS and again because of this sum here, which is not well known experimentally. Okay, it's known to within 1%, but then, as I said, this propagates it's a very large uncertainty when you extract alpha S, because these terms again are very small. Okay, yeah, you see it here. If you enforce CKM unitarity, namely you set this sum to be 2, then you get a parametric uncertainty driven now for the W driven by the W mass and by alpha S of 0.03 for the W as for the Z. So the first thing we did is to incorporate all these electroweak corrections to the Z, and then we did another thing. It is interesting also because a couple of years ago, these people reanalyzed the lab data, and they realized that there were some luminosity biases at lab times that were not accounted properly, and then they provide the corrections. It's a few per mil correction, but still it changes the experimental value. And so now we have a slightly changed experimental total width, ratio of hadronic to leptonic width, and peak hadronic Z cross section. And we have also new theory results from these extra corrections that we included. So voila. So let's see what happens with the decays. This is the update. What we did now is we did again a combined fit of the 3 Z boson seed observables and then the full standard model fit. Those are shown here. First thing to realize is that if you check the PDG today from the Z boson seed observables, you have these dash parabolas for the alpha S. So the 3 of them are consistent, of course, but they are scattered around the world average. Okay. Whereas now, if you use these new corrected experimental values, which are corrected at the few per mil, but still, suddenly you realize that all of them now, this is the full line, the 3 seed observables give a very consistent alpha S. So that's nice. That's even a very small change in the central values of these 3 seed observables leads to a coalescence of the alpha S derived from each one of these seed observables. So that's the first result. And our extraction is 0.1203 compared to the PDG today, 0.1221. The uncertainty is basically the same. And we did the electroweak fit, and this is the result we get, 0.1202 compared to 0.1194. So the uncertainty is the same, but we have a somehow larger value. But now you realize that the full SN fit and the fit of the 3 electroweak observables is basically the same, is identical. We have much better agreement now than before. So this is, so including the new electroweak corrections and including the new experimental data, now we have an alpha S extraction from the Z boson and from the full electroweak fit that is consistent. Okay, it's consistent. I mean, those two are consistent too, of course, but it's much more in agreement now. That's the first analysis we did. The second thing we did is we extracted alpha S now from hadronic W decays, including the more data compared to the work of 2016. What we did now is to include the total width, the ratio of hadronic to leptonic, and the hadronic widths. And we realized that we don't have a parameterized expression of the W boson leptonic, hadronic, and total widths. So in the literature, it doesn't exist. Of course, we have the analytical results, but we need to parameterize those in order to extract to the fit. So the first thing we did is to parameterize those, and you see all the parameters here for the hadronic and leptonic width. So if any of you wants to do an electroweak fit, now you have here the state-of-the-art expressions for the W boson seed observables. And using this, also we at full N3LO and including N3LO is alpha S to the 4, electroweak alpha, and then mix QCD corrections from Cara et al. From 2013. We evaluated numerically the value of these W boson observables. Just to give an idea, this is the value that you get in GFITR today. This is the value of the total hadronic, the total width of the W boson now in the, if you run GFITR, you get 20,091 MeV. What we find is 20 MeV larger, basically, or 30 MeV larger. For the experimental CKM, if we enforce CKM unitarity, then you get basically the same. There's a change of 2 MeV, but within uncertainties is consistent, of course. Now, what we did now is compare this work, these parameterizations to the experimental data. Sorry. And then we extract alpha S again. So we did first without enforcing CKM unitarity, we extract alpha S is 0.044, sorry, plus minus 0.005. So it's completely unconstrained. You see the parabola here. It is here, not here. It's of course consistent with the world average, but you see here it's a huge uncertainty. Now, because we have this large parametric uncertainty. Now, if we enforce CKM unitarity, now then we get this parabola. Okay, we get 0.101 with a 27% uncertainty. Okay, and this is the world average today. So we improve the precision from what we had done 5 years ago. It was 35% with CKM unitarity. Now it's 27%. So adding the extra seed observable of the total width improves things. But of course, still, this is not competitive today. Now let's see, but we did all this effort to really know what we can do with the W boson, because we want to determine, we want to know how well we can determine this from future E plus and minus machines. So let's go to this. Right now we are working on the future circular collider at the at CERN, the idea is to run at the Z pole and the W boson and produce 10 to the 12 Z's and 10 to the 8 W bosons. So basically, with these statistics, which is huge, I mean, you have 0 statistical uncertainties, and then you only care about theory and parametric uncertainties, basically. And then again, you have also not only Z and W, you have jets to do event shapes or jet rates. You have taus also, 10 to the 12 from the Z boson decay. So you from this also we will be able to extract with such a machine. We'll be able to extract alpha S with 0 statistical uncertainty. Basically, we have that now to deal with systematics and parametrics and theory. Not only we have a huge statistics, but we have a very small systematic uncertainty, because basically what we do is threshold scans in the Z case and also in the WW, and we have a very precise control of the center of mass energy of 100 kiloelectron volts, and this is conservative. Currently, we are discussing getting to 25 kiloelectron volts for the Z boson center of mass energy and 300 kiloelectron volts for the W1. So basically, this brings to a ultra precise systematic uncertainties in the not only statistical but also systematics in the extraction of the total widths of the W and the Z. So what we did then is to assume that we're in FCC EE with 10 to the 5 times the Z pole statistics, and with exquisite systematic and parametric uncertainties, and redo the fit, and we go from this parabola, which is what we obtained before, to this one here. Okay, basically we arbitrarily set it to the same value that we find today, but of course now the uncertainty has been reduced by more than a factor of 10, a factor of it goes down from 2.3 to 2 per mil, basically. At this stage, with these levels of uncertainty, you have to care now about the theoretical uncertainty. It has to be reduced by a factor of 4. So we will need N4LO corrections as well as alpha cube. Alpha cube. We have them. This is a typo. We have mixed QCD electroweak corrections of at higher orders that are missing. And voila, that's our prediction. We did the same exercise for W decays. Again, we have 10 to the 4 times what we got from Lab 2 in terms of W boson samples. So this basically statistical uncertainty is negligible. We have also an exquisite systematic and parametric precision, also because we will have 10 to the 12 D mesons. So BCS will be determined very accurately. So which is the leading parametric uncertainty. And also the W mass will be determined within tiny uncertainties. You see it here. So all in all, we will get, so at this stage, we have to worry about theory uncertainties that should be reduced by a factor of 10. Then here we need the electroweak corrections, alpha square and alpha cube that have been computed for the Z. This should be computed for the W, as well as N4LO and then mixed corrections. So with this, we will obtain an extraction that we arbitrarily set to the current world average of 1179 with a 2 per mil uncertainty. This includes everything, theory and experiment. So this is my summary. What I presented today is two things. First of all, I explained you that the world average QCD coupling has 0.85 uncertainty today, and that many of the observables that led to these are based on plus and minus data. The current C and the C base alpha S extraction has a 2.3% uncertainty. If you do the same for the W, we got a few years ago 35% uncertainty. Now the new thing I showed to you today is that we updated the Z boson with higher order electroweak corrections and also corrected lab data, and we extract this value of alpha S from the three Z boson seed observables with 2.3% uncertainty, and also from the full standard model fit. And we also determine what is the current theory and parametric uncertainties. You have them here. For the W boson, we did a new N3LO fit to also do the total width, and this reduces from 35% to 27%, but still this alpha S extraction is not competitive. But we have all the tools now ready, so that if we have a machine like FCCE with 10 to the 12 Z's and 10 to the 8 W bosons, we will get to extractions with 1 per mil experimental uncertainty. And if the central value remains the same, you will see that now there will be an inconsistency here. So if, of course, arbitrarily we set alpha s to the current average, if we get this result from the W boson and we get this result from the Z boson, it's clearly that those are not consistent. And this is one sigma line you see here. So, okay, yes, those are not consistent. So this will indicate some problem. In this case, there would be some contributions to the Z boson, for example. So this is a very strong standard model stress test. Voila, that's what I had today to present to you. Thanks for your attention.
Wonderful. Thank you very much, David, for this very interesting presentation. Do we have questions? From the room here.
Hey, David, probably you're not the person to answer this, but what is the prospect that the alpha s to the 5th term will be calculated? Right?
Yes, I don't know. We have experts in the audience that can answer. In principle, when we discussed this in the last in 2019 here at Trento with the experts, the people that had computed alpha s to the 4th, they say that it was in principle feasible. It's to compute alpha s to the 5th. But exactly, I don't know what time scale is in terms. So maybe people know now. Somebody knows here. Anybody working on?
Probably seeing some Russians are working. Do we have our questions from Zoom? So let me ask you a question. When you quote this 0.1, 0.2 uncertainty that you had, what is the dominant? What did you assume is the dominant uncertainty left?
Yes.
And also, what did you do with theory here? Somehow
yes, we assume, yes, theory, what I assume here is that we reduce the theory to be commensurate with the experimental uncertainty. So it's this 0.2 basically 0.1 experimental and 0.1 theory percent. So what I said is that in order to match the experimental uncertainty, we need to we need to reduce this by computing these things. So now is equal. I assume both to be equal. Now there is an open issue, which is we need to really confirm that the systematic uncertainties are at the 1 per mil level too. So, but in principle, we trust that. Some people also ask me, how come the W and the Z you get the same 1 per mil if we have much more Z data? And this is true is because we assume that we know the total. We were conservative here. We assume that the total width will be known to width of the Z boson will be known to within 100 kiloelectron volts, whereas for the Z we assume for the W we assume. Let me see. Maybe is it, 1 MeV. Anyway, this. Sorry, I am not sure about this value anymore. But this 100 kiloelectron volts is conservative. Because people are planning to get down to 25 kiloelectron volts. So if we determine this with 25, then this will be not at the 1 per mil experimentally, but it will be at the 0.05. Sorry, 0.5 per mil. Experimentally.
Okay. Thanks. I don't see other questions. So thank you again, David.
Okay, thank you very much for the invitation to participate. Yep, thank you. That would be much better. So thank you very much for the invitation to participate in this talk. I will talk about the alpha s determination from soft parton to hadron fragmentation functions in QCD jets with main focus on on jet fragmentation and on gluon radiation out of the leading parton initiating the jets. So that will be the outlook of my talk. So I will mainly focus on the Barton cascade and on the related resummation schemes that have been actually developed during the past 3 decades for the account of infrared collinear singularities of such gluons via such resummation schemes, which I will define throughout talk. So for example, we have the main one or the dominant one given by the double logarithmic approximation for Bremsstrahlung gluons. Then we have a modified leading logarithmic approximation, and then some extensions which we have been developing in the last years on the next to NNLO resummation. So from there, we actually will have to explain the combined scheme that we developed from the next to NNLO and the lab evolution of fragmentation functions by accounting for recent resummation of small x contributions at the next to leading order level from, for example, splitting functions that have been developed and that have been very useful for the completeness of such works. So then, instead of using for our fits, instead of using standard or regular parameterizations as AKK or KP, we'll use another parameterization for the fragmentation function via a distorted Gaussian that we are going to explain as well. So we explain that we express that distorted Gaussian in terms of 5 different moments. So they are the mean multiplicity, the mean peak position, the width, the skewness, and kurtosis. Then we compare with the plus-minus annihilation data and DIS jets data sets from 2 to 200 GeV. And then, of course, finally, the computation of or the extraction of alpha s out of that data from the moments. And then Diana will actually say how we'll continue this work, because this hasn't been finished and is a work in collaboration with David Denteria. So that's the current state of the art of the alpha s value and related uncertainties, which has been discussed many times in this workshop. So as everybody knows, the QCD coupling constant alpha is the less precisely determined among the coupling constants of the standard model of particle physics, and everyone knows why is it so important to reduce such uncertainties. So that's a page that was actually taken from the particle data group review. So you can see on the left the fragmentation function expressed by this humpback plateau, and in the left, in the right panel, we have the mean peak position or maximum peak position evolution. So you can see on the right how, as the energy increases, the mean peak position is actually shifted towards the left in a logarithmic scale, where we have introduced that parameter, where that parameter is introduced log of 1/x, so Feynman x, in order to highlight the soft fragmentation region, so we can actually distinguish the distribution from the hard fragmentation region on the left to the softest part on the right. And so we see that from that our motivation actually came from the nice agreement of alpha s with a standard with the expected value, where the only one or the only free parameter that was actually determined from the fit was lambda QCD. So now I will introduce jet fragmentation in perturbative QCD. So the main focus on perturbative QCD. So of course we have to consider hadronization as well in the frame of the local Parton hadron duality. So for enough inclusive observables, this hadronization will have been so very successful on the description of the Humpback plateau, as you saw. and on the maximum peak position of the fragmentation function. So the parton shower evolution is actually ruled by leading log contributions that can be cast in perturbation theory. And for the fragmentation function at the lowest scale, where Q0 or the collinear cutoff parameter or quark effective mass quark can be taken down to lambda QCD, the fragmentation function can be set to a delta function where we are just saying that we are assuming that local parton hadron duality or a one-to-one correspondence between the parton and a hadron. So in the end, the parton fragmentation functions are actually normalized to hadron distributions modulo an overall constant factor KCH, which normalizes the number of charged hadrons to of partons to charged hadrons. So the absolute normalization of the distribution can actually be adjusted by such a constant. So we see, well, that can be applied to many different type of process, like in the plus and minus annihilation, but also in proton-proton collisions. So one of the main characteristics of intrajet development is that property of angular ordering that make up the internal jet structure. So we have in this picture how the cascade should evolve towards the hadronization scale from the hard scale of the process. And we have to consider all soft and collinear, and then collinear singularity, which should be resolved through either DGLAP, leading logarithmic approximation, evolution equations that actually are successful at large X. So those will actually account for, such leading logs will account for hard emissions inside the cascade, but such are actually suppressed compared to the ones that are actually ruled by QCD coherence or soft fluent emissions, which are both soft and collinear. So then the other ingredients are, of course, the leading order splitting functions that the lab splitting functions that are known by everybody. So let's go to the different resummation schemes. So the leading one in the double logarithmic approximation, where soft and collinear gluons contributions are the main contributions, and they are resummed actually to all orders, as you can see through the anomalous dimensions on the right. So it's a main ingredient because soft gluon radiation determines the bulk of multiparticle production in QCD jets, but it neglects recoil effects, so it neglects energy conservation. So we have the anomalous dimension, which in that case scales like the square root of alpha s. So you can see the double logarithmic contribution from the hadron cross-section in this expression. Then in the modified linear logarithmic approximation, that such recoil effects are actually partially restored by including such collinear splittings coming from the hard fragmentation region. So they also actually include alpha s running coupling effects, which are actually proper to this resummation scheme. And then you can see how we start adding terms to the anomalous dimension of relative order square root of alpha s by exactly accounting by the expression of the splitting functions PQG or PGG. It depends on type of fragmentation you have to consider. So such are called single logs. And then we can go further and further, adding much and much terms, and then diagonalize, of course, the lab evolution equation following the Burr's approach or the Mueller-Doxy-Serre-Cassé approach, by including more and more terms which will further improve such recoil effects and count of energy conservation. and also running coupling effects. So we can actually make use of the alpha S renormalization group equation in order to include such effects as well. So we actually lead to that expansion in half powers of the coupling constant, which actually arises from the shift in log of z that is actually neglecting for hard particle emissions in the deep inelastic scattering, while, for example, computing particle distribution functions. So in the MLA approach, that's a bit different because we have to consider soft gluing emissions, and that amounts for actually integrating such double arithmetic contributions in the anomalous dimensions, and of course, they should be resumed to all orders in perturbation theory. So we have that picture where trigger one hadron. So the exclusive distribution. So the equation allows for the computation of the inclusive distribution of that hadron of energy fraction x, and then well, the insertion of alpha s into that equation may be solved in perturbation theory. So after passing, well, diagonalizing and passing into Mellin space, we get that equation where, for example, we have the first term on the right-hand side accounting for the double arithmetic approximation, then the second term accounting for single log corrections proportional to that A1 constant, hard constant, and then we have a third term, A2, which actually provide next to MLA corrections, which better account for energy conservation. So by replacing that ansatz in the previous equation in Mellin space, we can get a quadratic equation on the anomalous dimension, which can be solved perturbatively, as we did in that work. So for instance, we get from there the next to MLA anomalous dimension, where all the three types of contribution written in the bottom, in the block down, should be resumed to the free half order. So we end up with the anomalous dimension at that level of accuracy next to MLA. So the star in the last term stands for the fact that we don't so far account for next to leading order splitting functions, which are actually non-net to commute beyond leading order. So that's problematic for the diagonalization, and that should be one of the further steps that should be actually carried out to continue that work. So we have the DLA, for example, DLA anomalous dimension, then the MLA part, where we have a hard correction and one proportional to the beta zero coefficient of the beta function. So meaning that we are actually accounting for energy conservation, but also for running coupling effects in that scheme. And finally, well, more terms combining hard corrections, mixed of hard corrections with running coupling effects on beta null and beta 1. And then finally, that new correction proportional to A2. So all of those terms are of order alpha s to the free half. So then we actually tried some extensions aiming at matching the next to MLA anomalous dimension with what is actually known from the MS bar scheme. So in 2012, so we have that reference there. The splitting functions or next to leading splitting functions were actually resumed in the small x region, the small x region, exactly. So we have no singularities from such contributions, but still the diagonalization approach was a bit cumbersome, and we actually did some hybrid combination of the next to MLA approach and the next to leading log approach, also accounting for, in that case, for next to leading order MS bar running coupling. So within that frame, which we start here with that star, we included all contributions in the P2 part, or alpha S free half correction. So we have those new A3, A2, A4, and A6 corrections coming directly from the next to leading order splitting functions, while all the rest are actually coming from the expansion of leading order splitting functions at leading order splitting functions to the given power, contributing to alpha S to the free half. Then everything is written in terms of this S function defined over here. So let's start with our parameterization for distorted Gaussian, first introduced by Fun and Weber in the beginning of the 80s for the description of the lab data on the Hornbach plateau. So we have that parameterization, which with delta, so you can see the mean multiplicity, the mean peak position, dispersion, skewness, and kurtosis, which mainly affect the tails, will affect the tails of the distribution, while we'll put a main focus on the jet multiplicity, the mean peak position, and the dispersion. So we see that how to cast such moments, or distorted Gaussian moments, from the anomalous dimension that we just computed within that scheme. So such are the fits in the limiting spectrum approximation. So I just remind that that's in the limit where the collinear cutoff parameter can be taken down to lambda QCD. Well, the picture that actually proved very successful while describing the Hornbach plateau I showed in the beginning, and which proved that the local parking hadron duality is actually successful for enough inclusive observables in QCD jets. So we have the fits. And then we computed, well, first we computed the final, well, the expressions for those moments, multiplicity, average, peak position with skewness and kurtosis as a function of these two parameters, y. So that could be related to the center of mass energy, square root of S, and lambda, which is defined as the log of Q null over lambda QCD. Of course, in the limiting spectrum approximation, that parameter will be set to 0, but such expressions, as they are written there, can actually allow for the consideration of the scaling effects to see how they will actually impact the fits to the moments and the extraction of alpha S out of there. So in the limiting spectrum, where Q0 can be taken down to lambda QCD, the previous formulas can be reduced to those written there, and we are left with only free parameter that would be lambda QCD, which can be extracted from fits of experimental E plus E minus annihilation and electron proton, so deep inelastic scattering jets into hadrons data. So first of all, we see how the distribution is actually modified by the interaction of mass or hadron mass effects. So as you know, we have a mixture of pions, kaons, and protons. And actually, by doing so, it can be proved that the best agreement is actually reached for 140 MeV, so which is actually consistent with the dominant pion composition of the inclusive charged hadron spectrum. So you have the goodness per fit and the fits, and so from 2,2 GeV to 206 GeV for the different experiments on the plus minus annihilation. So finally, the extraction of alpha S from such fits. So the experimental distribution is fitted to the distorted Gaussian parameterization that we showed in the previous slide as a function of psi, so the log of 1 over phi min x in the range from O to y. So you have the definition of y there as the log of the square root of s over twice lambda QCD. So the root of square of s over 2, meaning the energy of the leading parton initiating the jet. Then we have the cross section in the left formula, where you can see the KCH factor normalizing the number of parton to the number of charged hadrons that will allow for the adjustment of the absolute normalization of the multiplicity distribution and also of the cross section, and the coefficient function, which is just given by the ratio of both QCD Casimirs. So each fit of the distorted Gaussian have 5 free parameters: maximum peak position, total multiplicity, width, skewness, and kurtosis. And each parameter or a component of the distorted Gaussian can be derived from the fit for each data set. So we have first 34, so with with an effective hadron mass of 140 MeV, 34 plus minus data sets at center of mass energy from 2,2 to 206 GeV, which amounts for 1,200 data points. So we can see for increasing energy how the peak actually shifts to the right, how the width of the distribution increases, while they keep moderate non-Gaussian tails. So the shift to the peak towards the soft fermentation region is actually a consequence of recoil effects and energy conservation, which comes from QCD coherence effects in that region of the phase space where gluons can actually interfere destructively. So that's why we see that depletion of the distribution in this region. So we get excellent fit at all energies with 5 free parameters of the distorted Gaussian given by the charge multiplicity, the maximum peak position dispersion, skewness, and kurtosis. Well, that was for the plus and minus simulation. Now for the deep inelastic scattering, where also jets are can be collectively produced in the Rickle frame. So we have 15 data sets from ZUS, from 3,8 to 173 GeV, which amounts for 250 data points. So all the measures are H1 ZUS and moments added to global fit. So we get excellent fits to the distorted Gaussian, but with much larger entities that in the plus minus case. So first fit of energy evolution of the first and second moment. So on the left panel, we have the multiplicity or charge multiplicity distribution in the limiting spectrum. So you can see, or you can check the values of alpha S in both plots, the value of KCH, the normalization factor, and the goodness per fit value. So you can see how the multiplicity or the charge multiplicity increases as the energy scale of the process increases. And on the right, the evolution or the energy evolution of maximum peak position towards from 2,2 to 206 GeV. So very nicely described after the inclusion of further logarithmic contributions going beyond the one that was actually done in the MLA and shown in the first slide of the talk. The theoretical, well, I also mentioned the fact that the theoretical MCH is absolutely normalized to match the data, and that's based on the local parton hadron duality, which actually proved successful for such inclusive observables as the one we are describing here. QCD coupling drives devolution. So we care about the shape, not about the absolute normalization. So very good agreement between E plus minus, DIS, and theory for the energy evolution of the fragmentation functions and the fragmentation function charge multiplicity and peak position. And then DIS multiplicity lower than E plus minus, but with larger eccentricities, as can be seen in that part of the plot around 100 GeV. So then it's time for the skewness and dispersion of the distribution. So you can see how the dispersion increases as well as the energy scale of the process increases. And for the skewness, we have much larger uncertainties. So in our case, the kurtosis was actually excluded from the analysis, since not really profitable for the determination of alpha S. So maybe the modification or that social impact on the tails is not so important, since we are actually focusing on the Gaussian shape of the distribution. So then from each fit, a different value of lambda QCD and of course a different value of alpha S can be extracted, as you can see on each plot, the previous plot and this plot. And then an average value can be actually cast out of there. So we can see with chi-square increasing, averaging, increase uncertainty for few point fits to reach goodness per fit on the order of 1. And the final alpha S uncertainty is of the order of 1.2%, including hadron mass effects, experimental fits, and correlations. So in order to assess the scale of variation, so for example, we can actually take the limiting spectrum where Q null is set to lambda QCD and subtracted from 1 GeV, where we decide actually to stop. We decide to stop the cascade at 1 GeV. We get like 2% of due to scale variation. So which is quite encouraging for the rest of the evaluation and future work. So from there we can see the value of alpha, the average value of alpha S that was actually obtained from this analysis on the distorted Gaussian and the fragmentation function moments. So we can actually conclude from this scheme, a novel precision measurement of alpha S at this level of accuracy within that scheme. And then a final outlook to see what's coming next, because as you know, we have or we need to have in the end a lambda, an MS bar lambda. And we have actually to work within the maximum subtraction scheme. So ideally, the resummation scheme that should be actually implemented for full consideration of this computation of alpha S is the N4 or next leading log resummation scheme for the diagonalized anomalous dimension. So which means we need an MS bar diagonalized anomalous dimension in order to get MS bar fragmentation function moments as well. So we have, for example, that well, the MLA was actually the first, well, one of the first calculations were actually done in the massive Bloom scheme by Alfred Müller. And it was actually found that the anomalous dimension or DLA anomalous dimension I showed in the beginning coincides with the one that was actually found in the past decade by Vogt within the MS bar. So no problem for the first term. This term is actually scheme independent at leading order. But then the problem starts when we start considering higher order corrections. Like, for example, we have terms which are proportional to the beta function, and such terms shouldn't appear within an MS bar scheme in the anomalous dimension. So they will actually appear into the coefficient functions. So ideally, what we need to do further is that we can, or we should obtain all of those terms from the MS bar scheme using Vox resummation from this reference, and the exact generalization that was actually recently proposed by Karikov and Tereyev, who I want to thank for the discussions we had, and then repeat the steps of the second item to cast P3 and P4 within the same MS bar scheme. So then, in order to maybe we can actually match in the future the NNLA approach with the MS bar, current regular MS bar, as it was actually pointed out in that paper by Dufnail, where the main difference actually from both for both anomalous dimensions come from terms which are proportional to the beta function of the renormalization group equation. So finally, so what we have to do, or what we've got left to do, so including all of those terms, and then next to leading log, free leading logs, and finally N4 leading logs. So we will have a series of that kind anyway. So for example, some of those terms were also determined by Vox. So you can see contributions which are alpha squared suppressed, and then contributions which are alpha s to the 5th half suppressed. And finally, the conclusion. So the anomalous dimension was obtained from the mixed resummation of leading order standard splitting functions and next to leading order corrections to the splitting functions. The moments, multiplicity, maximum peak position, dispersion, skewness, and kurtosis of the distorted Gaussian were obtained at the same level of precision as a function of the only free parameter lambda QCD. The theoretical mean multiplicity was absolutely normalized to match the data. Well, that's based on the local partner hadron duality. It cares about the shape, not the absolute normalization. Very good agreement between the plus and minus annihilation data, DIS data, and theory for peak position and dispersion. So that's the value of alphas that we get from the hybrid method we developed. And for the outlook, so matching the next to MLA or MLA resummation with the MS bar anomalous dimension from Vox resummation and exact diagonalization of next to leading order splitting functions. Thank you.
Okay, thank you very much for this presentation. Do we have questions? We have time for maybe one quick question. I see one. Okay.
Sorry, no, just there was a typo here in the conclusions. It's NNLO approx. The alpha is quoted here is NNLO approx.
Yes, NNLL plus NNLO.
Approximately, yes.
Yes.
So in slide 28, you mentioned that you increased the uncertainty in some of the points to make the chi-squared over DOF of order 1. What do you do exactly then?
I think David can answer that question because I didn't make fits.
David?
Yes. In some cases, we had to enlarge. So we used the PDG-like approach of. So we had in some of the fits had large chi-square. So what we did is we enlarged them in some cases to have a chi-square per degree of freedom of order 1. So this just indicated that some of the uncertainties were underestimated. But this affected a few points only, and I forgot now. I can check. I can send you online the details. This is only for. I mean, DIS is okay. I mean, DIS does not have any issue because the uncertainties are large, but E plus E minus data in some cases had too small uncertainties, so we enlarged some of them. I think this was for the peak. So the top right, I think we had to enlarge in some cases in order to get a good chi-square.
Mainly for, I think I remember for DIS was more, right?
Yeah, of course, because yeah, the uncertainties from DIS are large. So the fit works nicely, but of course the uncertainty of the alpha is derived from the fit is. So if you use, we did the fit using DIS only, and of course the precision is much worse than what we get from the E plus E minus data. From the E plus E minus data, we have basically 1% type of 1.2% uncertainty. But as I said, in order to get a good chi-square, we had to enlarge some uncertainties that were too small.
Okay.
I can give you more details offline if you want to know which. I think was the peak that was too small.
Okay, we really have to move on now to the next talk. Okay, thank you very much. Yes, wonderful.
So you hear me? Sorry, you also see my pointer, right? I assume you see my pointer.
Yes, we do.
Okay.
Yeah, but we see it.
Okay, great. So thank you very much. This talk will complement a little bit the seminar by Johannes Weber on Monday, but I will make a bit more emphasis on the estimate of perturbative uncertainties, and you will see also how to get experimental values from real experimental data. This is done in collaboration with Diogo Boito, and these are the two papers you can look at for more details. So the outline is giving you some motivation and presenting the theoretical framework. Then I'll discuss the main idea that allows you to compute to get alpha s from moments. And then I'll present this perturbative analysis, experimental data, give you finally the results and conclude. So if you want to measure the strong coupling in perturbative QCD, probably this has been discussed 1,000 times already, but let me emphasize again, you need some observable that fulfills these requirements. It must have a small non-perturbative power corrections, and you should be able to compute it to high order in perturbative QCD, and hopefully you have a series which has good convergence. It should be very sensitive to the strong coupling, and its typical energy should not be too high. Then when you run, then you can benefit from this run up shrinking of the error. And it should know experimentally or via lattice with high accuracy. And it's not simple to find an example that satisfies all of this. And I will show you an example that actually fails. So bothonium masses actually do satisfy all of this, and we have this analysis in this article. And the perturbative formula that describes very well data, if you stay within principal quantum number smaller than 3, it's a perturbative series which is proportional, of course, to the pole mass. And it's known to 3 loops, which means alpha is to the fact. So you might, and it's nicely convergent. So you may think this is an ideal place because we know it starts at order alpha squared, and then you know a lot of terms. Of course, if you want to do real phenomenology, you cannot use the pole mass. You have to use some low scale short distance mass. And in our analysis, we use the MSR mass and include of sorts of funny effects like finite charm mass and so on and so forth. And then we decided to make global fits. Of course, our main analysis was to get the bottom mass, and we did. So we took, as I said, every experimental point, which essentially have 0 uncertainties. But we took all of them that had the principal quantum number smaller or equal than 2. What I'm going to discuss is if one is too ambitious and wants to determine not only the bottom mass but also alpha strong, you get a value which is good, but it's not great, because as you see, the perturbative error is a bit large for what's expected these days. And you can trace down the problem to having a very, very strong correlation, theoretical correlation in between these two parameters. So and this problem remains the same if you want to use experimental input for the bottom mass. So I think that to the previous list that I showed, one should require, in addition, that the observable should be only loosely dependent on other parameters if they are not known very accurately. So let me talk a little bit about the theoretical framework of QCD sum rules. So one starts with the so-called vacuum pluralism function for massive quarks. This means that these currents are heavy quark currents, and this is the kind of diagrams that you have to compute to get pi. But it is, if you subtract it once, you can relate this function, this mathematical function, to the total hadronic cross-section R, which is something that you can access experimentally. Now, if you Taylor expand both series, here the Q squared you can pull down and just use the L'Hopital rule and so on and so forth. What you get is this relation. You get that these weighted averages of the experimental total hadronic cross-section, which you can again get numbers for just looking into data, can be related in one-to-one with the Taylor coefficients expansion of this guy around very small values of Q squared. And that's what you do. You just measure experimentally and compare to data. What's the key idea for getting alpha S? Well, let's do the classical thing, which is simply computing the moments in perturbation theory, just taking, as I said, Taylor coefficients of the pi function. And the first thing you notice is that you will have a very strong dependence on the heavy quark mass. It goes stronger and stronger as you take higher and higher moments. And this means that you have a very high sensitivity to the quark mass, and this is a great place to fit for the heavy quark mass. As you see, I have an expansion in alpha S, but I have two renormalization scales. One, mu m, which is related to the scale typical of the ms bar mass, and mu alpha, which is the scale associated with the evolution of alpha strong. And what we showed, we showed in this article that if one wants to have order by order convergency, you better vary the two of them independently. This is also known to relatively high order, alpha S cubed, for both vector and pseudoscalar correlators, which are both relevant for this talk computed in this series of papers. Also, power corrections are small, but they are known, and they are known next to leading power and also next to leading coorder. We just use this as an estimate of power corrections, and they have a very, very small effect. What's the idea? Well, we want to lose sensitivity to the heavy quark mass because we want to fit for alpha strong. So the first thing you do is you take each one of these moments and take the nth root. This will convert the dependence, instead of being to the power of 2n, it will be to the power of 2. Now you take two consecutive roots and take the ratio, and immediately you will lose the mass dimension of the observable. This prefactor will cancel out along with the dependence on the mass, because now it's going to be pushed to logarithms that are damped by 2 powers of alpha strong. So even if we don't know the quark, the bottom or the Charm mass very accurately, it's going to be such small dependence that you can still use this very nicely to get alpha strong. So this trick is going to be used for the vector correlator, in which you use real data, and also for the pseudoscalar using results from lattice QCD. And so we'll do so and reanalyze lattice data doing this double scale variation to get more conservative uncertainties. So let's go to the perturbative analysis. This is just an example. This is the second moment ratio for Charm. You can see, as I promised, that you are clean from masses up to order alpha S, and only at order alpha squared you will get the first time a log of the mass. Now we take upon the idea, which was first introduced in this article, and in principle want to vary the two scales independently in order to make sure that you are properly estimating the uncertainties and you have order by order convergency. But we are going to rethink the strategy, because we don't want, because you will have logs of the ratio of the two scales. And even if you stick within this regime, which makes sure that there are no large logs of the mass over any of these mu's, you don't want to have large logs of the ratio of the masses. And the common law is to limit the value that this argument of the logarithm can take. Normally you take it between 1/2 and 2, but we'll study the dependence on this parameter side. So this is the kind of isobaric plots that you can do. You can study how the result of the structure alpha S depends on the value that these two scales take. And as you can see, it is very important to vary the two of them, otherwise you can underestimate your uncertainties. I'm showing the shaded areas here. These are the regions of the double variation plane that you exclude. Of course, you can always take them equal. This is the same as taking psi equals 2. And if you carefully look into what kind of lines you cross, you will see that you underestimate your errors by a factor of 2 or larger. So let's look this in one-dimensional slides. So if you are worried about the central value, it's not going to depend too strongly on the value of psi. This is always below the %. So I think this is very reasonable. What does depend strongly on the value of psi that you pick, and remember, we stop at psi equals 2. I mean, nothing on the right of this line is very relevant, but we wanted to see how it keeps evolving. You can see that the dependence on psi is almost linear. So you can gain a factor, you can enlarge your errors by a factor of 2 from doing the naive correlated estimate to what we do. What we make sure is that if you keep the standard psi equals 2, you will have very nice order by order convergency in all of the observables that we studied. Now is the time for data. You have to compute the moments, and this does not come out for free. It is a little bit complicated because it is built up of different pieces. Even before you start producing real charms, you have resonances below threshold that you can treat in the narrow width approximation, and this is known with very high accuracy. Then there is data on the continuum, and unfortunately, there is no tagged data on charm. You have data which has production of up, down, strange, and charm, and it's a plethora of experiments. And since you have to do integrations over them, the best thing you can do is combine data with some algorithm, and we adapted the algorithm of this gentleman and recomputed the moments that were originally done in this article. At some point, you stop having data. This is the point S max, which is around 10 GB, but you still need to do something about it. So what we do is cook up a model, which is perturbative QCD, putting as much information as you can with mass corrections, alpha S corrections, and assign a conservative estimate to it. And finally, because this data here has the things that you want and the things that you don't, you have to subtract. You have to subtract the background, and this you also need a model for this. So you use, again, QCD model for the up, down, and strange production of quarks, and assign again a conservative estimate. Now you will realize that we want to fit for alpha strong, and two of the pieces that go into these moments depend on alpha. So you have to consistently keep track of this dependence if you want to have a conservative, let's say, a kosher determination of alpha strong. So that's exactly what we do. So we have an approximate linear dependence of the experimental moments on the difference between alpha strong and alpha strong at the roughly world average. Now you will see that errors are surprisingly competent, and it is so because there are strong correlations. You are using the same data for the numerator and the denominator. Therefore, there are some strong correlations, which translate into some correlation, some cancellations that gives you small errors. You also can realize that the dependence on alpha S becomes smaller and smaller as you go to higher and higher moments because they depend less on the continuum. Now, bottom experimental data is just ruled out. It's off the table if you want to do something precise because it's just too large and the bottom mass is just too high. But for charm, you can have a decent determination. If you combine this with lattice data, which is also very precise, you have lattice from the zeros moment that exists for the pseudoscalar correlator and also on other ratios, you can combine all of these and get a very nice result for alpha strong, as you will see in the results. So let me show you first partial results. So we need to use some values for the masses. The bottom is not so important. You need this for the matching. To have alpha S at the Z scale, you have this value for the gluon condensate and for the charm mass. You crank it through. So the first thing we do is just use our real experimental data on the charm vector correlator, and you get these values for alpha strong for the first, second, and third ratios. You see that the values are very consistent. Two of them are very, very similar, and the third one seems to depart. So it's a very small trend towards larger values, but I would not say that this is worrisome. And what we did, we were just taking as our final result whatever comes out more precise. And this is an interplay between having a not too large perturbative error and not too large experimental error. We also realized data on lattice on the zeros moment. These are the different collaborations that yield results. We just used their lattice values on our theoretical framework and also on the first two ratios. These are all of the results are collected in this table. You can see that for the zeros, you can see that with our analysis, almost all of the results happen to have exactly the same uncertainty. And it seems that there is a tendency when you go from the first to the second moment, almost every analysis will drop down the value of alpha strong, and we don't know why this happens. And also, except for one or two analyses, we also find that our more conservative error estimate leads to larger errors as compared to what's normally quoted in the lattice articles. So let me show you the final results. I can give you first a number, which is only using experimental data, no lattice. As I said, this appeared already in the previous table. This is for the second moment. And we have, I would say, again, good, but not super great value. I think this is competitive. Of course, if we wanted to be naive and instead of doing double scale variation, we just do correlated variation, the error would go from 19 to 13, which is very, very close to the world average. But I think it's better to be on the safe side and quote the more conservative error. Now, the advantage of having lattice data is that there is completely uncorrelation. So lattice experimental results have nothing to do with experimental results on the cross section, and also because the series are different. One of them is pseudoscalar correlator, the other one is the vector. There's nothing that these series, the convergence of these series have nothing to do with one another. So you can treat experiment theory uncertainties also as uncorrelated, and then you can make a chi-square function that combines these two experiments. We took whatever is more precise from the theory side and whatever, sorry, from the vector correlator and whatever is more precise from the pseudoscalar correlator, make a chi-square function and do the fit again. And what you find is a very, very, very similar central value, but now the error has shrunk from 19 to 14, which I think is very competitive. Well, this is the plot that compares to other determination. It's already a bit old, but I think you can still learn from it. So that was all from my side. Let me just quickly conclude. So quantities which have high sensitivity to heavy quark masses are not ideal to determine the strong coupling, and this happens because heavy quark masses are not very precisely known. Taking ratios is a good strategy that allows you to lose sensitivity on this unwanted parameter. And we apply this to Charmonium Sum Rules. And I think we got good results. Series are nicely convergent as long as you are careful with your estimate of perturbative uncertainties. And you benefit from strong correlations between experimental values. We find a competitive value for the strong coupling. And I think that this strategy that we came up with can be used in a plethora of scenarios. You can use it to also to lose sensitivity, not only to the quark masses, but also, for instance, to some non-perturbative parameters. Thank you very much. This is all. Anyone there? I cannot hear.
I can hear you, Ichiti. Can you hear us?
Yes, I hope you heard all of what I said.
Yes, sure.
Oh, okay. Ooh, okay.
No, I think it's Ichiti star.
Can you hear us now?
Yes.
Yeah, I do.
Okay, sorry about this. Yes.
No problem. I just thought I was.
Should I?
Yes.
I don't know. You can.
There's a question from here now.
So,
Yes.
Hi, Gonzalo. Thank you very much for the presentation. I want to understand a bit better the thing of the perturbative uncertainties. In particular,
Yes.
when you are at the Charm scale, reducing the renormalization scale by a factor 2, is this possible? I mean, because you go to really very low energy scales.
We are not doing that. We are not doing that.
Okay, and related to this, I make you both questions, and then that's it. The scale dependence of the coupling doesn't seem monotonous, no? There is some kind of minima in these plots. I don't know, because I have seen them very fast. And if this is the case, I wanted to know. I mean, we have seen this in other cases, and I wanted to know what's your opinion on this. If this
Are you talking about these?
No, previous or next? I don't know. It was around there. Yeah, there. Yeah, okay. It flatters. No, it's not really a minimum. It's not really non-monotonous. But yes, sorry. Okay. So it was only about what do you do with the scale at the Charm scale? What do you do with the scale variation there?
Yeah. So we, in our analysis, the Charm mass is still a dynamical scale. So our alpha S runs with 4 flavors: up, down, strange, and Charm. So you never have to cross this threshold. This is to start with. Now, the typical scale of your problem is not, if you look carefully into it, is not the Charm mass, but twice the Charm mass. So what we do is we vary between half this scale, which is the Charm mass, and twice the mass scale, which is roughly like 4 times the Charm mass. Because this is like the production scale of a couple of massive quarks, if you think about it. Okay. So we never, I mean, So you never have to go to that to such low scales. And we also made lots of tests that I didn't show that perturbation theory. I mean, you can look into my articles with Bam and Denady and Andrejo, and there we have lots of plots in which we show that at the scales that we are studying, there is no problem with perturbation theory. Every time you add an order, you will get a reduction of, you get closer and closer to the true answer. So I don't think we have a problem with perturbation theory failing. What you may have is a problem of not estimating properly your uncertainties. And then it may happen that your 3-loop result is incompatible with the 2-loop and the 2-loop is incompatible with the 1-loop. That can happen if you correlate your scales.
Okay. Okay, yeah. Sorry.
You wanted to hear about this. This is not a dependence on the scale. This is a dependence on how much you cut off your plane. Right?
Okay.
So if psi is 1, it means that you cut everything but a line. If psi is 3, it means that you don't cut anything. Psi equals 2 means that you cut these corners here. So be careful when you read these graphs, because it's not a dependence.
Okay, related, one last question, okay, because I'm trying to understand this. I mean, I have read the papers, but it's a bit involved. So one thing about the scale variation, so this thing that the typical scale is 2 or 3 times the charm mass, I would say naively that it depends on which moment you are looking. I would expect that higher moments, in the end, they feel very low energy scales.
But you're absolutely right. So if you go for large n, then you enter into the regime of non-relativistic UCD, and the typical scale is the charm mass over n. That's why you have to stay within low n's. And we took the second moment because I think it is still safe. We made some other analysis in another article in the last beta not limit to study these things more carefully. And as long as you stay, if your n is order 1, then you can set n equals 1, let's say. And that's how we know that this is the typical scale. But you're right. If you go to higher and higher n, then you single out the narrow resonances, and then you can have duality violations because you are not properly taking into account the Sommerfeld effects, and you know what I'm talking about.
Okay, we have another question here.
Oh, thanks for a nice talk. What I wanted to ask is the lattice data that you used, were those all extrapolated to the continuum limit?
Yes.
Or to rephrase it, are those all lattice data that would pass flag criteria?
I don't know. I think they passed the criteria, but at least some of them. In the end, it doesn't really matter, because the error is completely dominated by perturbative uncertainty. So even if you want to double or triple the lattice error, it's not going to affect much the uncertainty of alpha S. So I think we're on the same side.
I'm not sure about that, but yeah.
Okay.
Thanks.
Okay, David, do you have a question?
Yes, it's a pity that you didn't post a slide, so I could not follow in detail. Can you please go to the PDG? I think it was the before last, the PDG average. This I see. No, in the PDG itself has a similar plot where you can see the category
here has been generated by myself, so I didn't steal anything from PDG. So I don't know which one you are referring. So
if you take a look at the PDG, maybe I can share it. But anyway, we have a 3.2% uncertainty. That's what they claim. This was included for the first time this year. Do you agree with such an uncertainty assigned? And how can we improve this? And how can we further reduce? One of the goals of this workshop is to, as you heard in the first day, is to find ways to reduce the theoretical or experimental uncertainties. So how do you see this?
You're talking about the average or
about every single. Let me share 1 second. Let me share the screen. Maybe
unshare. I
can do it. I can do it. I think I have host privileges. So
yes.
So how can this is what goes into the this is what our PDG conveners included this time. So
the question is whether what was presented now is already published in a peer-reviewed publication.
what I just presented is not included in the PDG review, but it's published, of course, and it's like almost 2 years old.
Is it from 2000? This is the result from 2018, right?
Which
So
one?
I doubt.
Wait, no. This is another paper. This is the quarkonium thing that I said is a bad idea.
Okay.
That's why it has such large errors, because it has a correlation, very strong correlation between the mass and alpha. That's why I said that it's a bad idea, right? Because it is depending on 2 parameters. The thing I presented is not in this table.
So what is the uncertainty that you extract from bothonium bound states? What is your alpha S? What is the value? Since I don't have your slides.
This was like it's like 0.005. It's not super great.
Okay, and the central value is consistent with the wall average, I suppose. But is it to the right, to the left?
Yeah. It is like almost on top. And you can see it there, right? This is the number.
This is the number. This one, okay.
This is the number I said is a bad idea. Yeah.
But your result is your new result is identical to this? That's my
no. My result is a bit slower, and it has a much smaller error. It is like 0.013. No, wait, what was that? I don't remember myself. It was.
Shall I move this to a discussion session later, maybe?
Yes, no problem.
Maybe it would be nice if you post your slide.
I will do it right away.
Okay, then we can resume the discussion later. Now we move to the next speaker, Alexandre.
Okay, very good. So thank you for your invitation to talk about alpha S extracted from a spin structure function. So I will.
Sorry, just to mention it, your slides are not uploaded either.
Yes, I will. I tried to upload them just before, but I didn't have the password, so I'll look into it right after the talk. So I will discuss measurement of alpha S from spin structure function. We've seen here those variables, so I don't need to explain them. I just want to remind you that I'm going to talk only about inclusive experiments. So that's a reaction where only the scattered lepton is detected, and we don't detect the target or a target fragment. So when we have an inclusive reaction, the cross-section can be factored as a first term that tells us about the point light scattering, and the sum of 4 terms that tells us about the target structure. The 2 first terms are the spin-independent structure function, F1 and F2, and the 2 last terms are the spin-dependent structure function, G1 and G2. So F1 and F2 are obtained when the beam and the target are unpolarized, while G1, and we can separate F1 and F2 by varying alpha and beta that are kinematic factor. And for G1 and G2, we need a polarized beam and a polarized target. The quantity are obtained by looking at beam spin asymmetry, and G1 is separated from G2 by varying the target spin orientation. So if we consider only the inclusive spin structure of the nucleon, alpha S can be extracted from several ways. The first one is to look at the Q-square evolution of G1. That's the most complex way. It involves doing a global fit of the data. It requires also non-perturbative input, the quark and the gluon distribution, possibly also other non-perturbative input like higher twist if the data are at low Q-square or large X. Another possibility is to look at the Q-square evolution of the moment of G1. It's a simpler task because the X dependence is integrated out, and the non-perturbative input are more or less well measured. Those are the axial charges of the nucleon, A0, A3, and A8. And again, maybe you need a higher twist if the data are at low Q-square. But the issue, the main issue with this technique is that there's an unmeasurable low X part that cannot be achieved in the experiment. To go to x equals 0, you would need infinite beam energy. So there's always a missing part. Furthermore, A0 is a Q-square dependent, so it's not that convenient, and may get a contribution from the gluon polarized distribution, although this depends on what scheme is used for the perturbative expression of G1, and if the MS bar scheme is used, there's no contribution from the gluon. And a third possibility is to look at the isovector part of this moment. So that's the integral of G1 on the proton is the same on the neutron, which is also involved in the Birken sum rule. So this isovector moment is called the Birken sum. This is the simplest way. And the axial charge A3 is actually very well measured at well below the sub-percent level. Also, the DGLAP evolution of the PQCD theory for the integral is known to higher order than in the single nucleon case, and there's no gluon contribution. Nevertheless, the low X issue remains that we cannot measure it, and also it's more complicated or more difficult to get this quantity experimentally, since it demands measurement both on the polarized proton and also on the polarized neutron. So in this talk, I will focus on this last method. That doesn't mean that the other methods are not competitive. This is just the focus of my talk. So the integral of G1 is often denoted gamma 1. So that's what I will use in this talk. And as I mentioned, the isovector part of gamma 1 is involved in the Birken sum rule. The Birken sum rule is telling us that gamma 1 p minus n should be proportional to the nucleon axial charge A3, or equivalently GA. This is the original Birken sum rule. You can generalize it for finite Q-square by including PQCD radiative correction, which are shown here in the MS bar scheme. And if you're interested at going at moderately low Q-square, you need also to account for power correction. And those power correction also involve alpha S, because each of the higher twist terms here have their own radiative correction. So once you consider the Birken sum, there's two possibilities to extract alpha S. You can do an absolute measurement of the Birken sum and solve the Birken sum rule for alpha S. That way you get one alpha S by experimental point, but this method has a poor systematic accuracy. Typically, you'll get an accuracy that is in the 10th percent, so it's really not a competitive method. The other method to extract alpha S from the Birken sum is to measure its Q-square dependence. Of course, then you need several data points, and you get only one value of alpha S, or a few values if you have many data points. But you have a good accuracy using this method. So for example, it was developed, used in the 1990s by Altarelli and collaborator. They analyzed the CERN and SLAC polarized data, which yield an alpha S that was quite reasonable for the time. So we use this method to extract alpha S from a spin structure measurement done at Jefferson Lab in Hall B. The experiment was called EG1 DVCS. It was run during the 6G era of Jefferson Lab, and it used the CBAF large acceptance spectrometer class. That's a spectrometer that covers polar angle from 18 to 48 degree, and that has a nearly full azimuthal coverage. We use fixed polarized target, NH3 and ND3 target, and the polarized beam. The experiment was actually not dedicated at measuring G1, but at measuring the DVCS reaction, which is an exclusive reaction. So we got more than enough inclusive statistics from this run. The run was 6 months at an average electron beam current of 7 nanoamps. So that means we got about 10 to the 17 electron on the target. So we used only EG1 DVCS data to extract alpha S in order to avoid uncorrelated systematic between experiments. And the reason for that is because point-to-point correlated systematics, such as the one coming from polarimetry or nuclear correction, are they have a minimal impact on the extraction of alpha S, on the uncertainty on alpha S. And the other reason we used only EG1 DVCS data is because this experiment largely dominates the world data in terms of statistics. A drawback from this choice is that it restricted the Q-square range, or Q-square range was from 2.3 to 4.7 GV square. While if we would have used the whole set of world data, we would have been able to go from 2 to 10 GV square. Now, when I say we used only EG1 DVCS data, that's not fully accurate because GLAB is at relatively low energy. There's an important part of the integral that are missing at low X, as I mentioned before. And this part is substantial for EG1 DVCS, but it can be estimated relatively precisely thanks to the higher energy lab that also measured gamma 1, like SLAC or CERN. And it will not be possible to make a reliable estimate of the Birken sum without those higher energy data. So this is a contribution that needs to be kept in mind. So here are the world data on the Birken sum up to 5 GV square in Q square. The GLAB EG1 DVCS data are shown by the blue triangle, and I use the 5 data points that are in the box for the extraction of alpha S. The error bar on each point is the systematic error. You cannot see the statistical error because it's smaller than the symbol. So we don't really need to worry about statistical uncertainty for this extraction. For the experimental systematic uncertainty, what we did is we separated the point-to-point correlated and point-to-point uncorrelated systematic uncertainty. And to do that, we fitted the data with the expected PQCD form, and then we used the unbiased estimate to assess the point-to-point uncorrelated uncertainty. So to do that, what we did is, that's the unbiased estimate, we just lower or reduce the experimental systematic uncertainty until the chi-square is 1, and we call this rescaled systematic uncertainty the point-to-point uncorrelated part. Then the point-to-point correlated part is determined so that the quadratic sum of the two is equal to the full experimental systematic uncertainty. For the low X systematic uncertainty, likewise, we separated it in a Q-square dependent and independent part. And for that, we assumed that the Q-square dependent part was proportional to the ratio of the unmeasured part over the full Birken sum time the local slope multiplied by the Q-square bin size. So this Q-square dependent low X uncertainty was added to the point-to-point correlated experimental uncertainty, and we used this sum for the chi-square minimization of the fit that ultimately yield alpha S. So we applied this method because it allowed to have a large part of the low X and the experimental systematic uncertainty to be suppressed in the determination of, in the extraction of alpha S. So in all, the leading uncertainty from this extraction is the point-to-point uncorrelated uncertainty, which gave about 4.4% contribution to the total uncertainty. Then next came the point-to-point correlated uncertainty, about 3%. To determine this one, we simply systematically varied the point within their point-to-point correlated uncertainty and redid the fit and look at the difference, and that what brings the 3% uncertainty. The other uncertainties were negligible. The statistics, as I mentioned, the twist for contribution, they turned out to be small, but we also started our fit at a relatively high Q square. We looked at the truncation of the twist, the Bjorken theory at twist 2, which yield about 1% uncertainty, as well as the truncation of the beta theory that we used to evolve alpha S from more relatively low Q square to the mass of the Z boson. So all those uncertainty are not leading. So the result of this extraction is as follow. Alpha S at the mass of the Z boson was found to be 0.1123 plus or minus about 5.5% uncertainty. And here I'm comparing to the then best world data when this was extracted, that means 2014. We also looked at what we would get at the tau mass, and that's the value we got if we evolved only up to the tau mass. So here you can compare this value at the tau mass with the extraction from tau decay. So you can see we have a quite large error bar, but that's not ridiculous. And here I'm comparing this extraction to the extraction available in 2014 from a global fit of unpolarized data. And again, we're a bit large, but it's a different observable. So we saw it had the value to do this extraction. Finally, here we are comparing to the other experimental extraction of alpha S. So what are the possible future extraction of alpha S, the same observable from Bjorken sum? At GLab, we have an approved experiment called DG12 that is using the upgraded class detector with the 11 GeV beam that is available since a few years at GLab. We expect a precision similar to G1 DVCS, but with a Q square, a larger Q square reach, and also with the low X issue reduced. So that's one first possible improvement. And then, of course, there's the electron-ion collider, and I will discuss this in the remainder of my talk. So I just did a quick exploratory look at what we would get at the EIC if we were intent to extract alpha S from the Bjorken sum. And that was just to see if such idea is worth pursuing. So what I'm going to present is a bit rough, but as I said, it's just exploratory. So according to the EIC white paper, this is the expected kinematic coverage of the EIC. You can see comparing with the present world data and the expected data from GLab at 12 GeV that the current X reach will be largely increased. And thanks to that, you can see how well we can measure the Bjorken sum at the EIC in terms of what fraction of the sum rule of the integral we can measure. So the black line is the full integral, and the red line is the part of the integral that we can measure at EIC. And you can see that up to 10 or 20 GeV square in Q square, we measure a large fraction of the integral. You can compare that with what we did at GLab with 6 GeV, with those data here in blue, red, and green, and what we expect to do with 12 GeV shown in magenta. So it may look that we're not measuring much at GLab, only half of the sum rule at Q square greater than 1, and then it quickly dropped after. But remember that we benefit from data from a high energy lab that allow to estimate quite reliably the missing part. This will not be the case for EIC, so the extrapolation will be much less guided. So we have to be wary about not measuring enough of the integral. So for this reason, a good place to extract alpha S seems to be in this range at a higher Q square, we will have too much low X uncertainty. And then at lower Q square, we may start to have too much uncertainty from a higher twist, although those will be measured or are measured at G-Lab, so we can consider going at lower Q square using those measurements. So for the uncertainty budget, for the statistic, I assumed that at the lowest relevant Q square, the statistical uncertainty would be 0.5%, and then at the highest relevant Q square for the alpha S extraction, the statistic would be 0.05%. And I'm assuming that we will not use those are raw data that will be available when the EIC data comes out. So following the expected characteristic or performance of the EIC, reaching this type of precision should take about a year. This type of precision you can compare with what we got at G-Lab, and that's about twice better than the statistic gathered for a typical doubly polarized experiment looking at inclusive structure function. So this is not too pushy as an assumption. For the systematic uncertainty, I assume a 4% uncertainty on the nuclear correction to extract the neutron for the deuteron. However, if we can tag the more or less spectator proton, then the nuclear correction will not contribute to the uncertainty. For the missing low X part, I'm assuming 100% uncertainty. Polarimetry is 3%. For the radiative correction, we'll have lower energy data, but still I assumed a rather conservative 6%. That's probably quite pessimistic. And for to get G1, what we typically do is we measured A1, and then we obtain G1 by multiplying A1 by F1 plus some perturbative correction. So we need to get F1, and F1 in turn we get it from F2 and from the R ratio. So for that, I assume that we will know F2 on the proton and neutron at the 2% level and R at the 10% level, and that gives us a 2.5% uncertainty on getting from A1 to G1. Actually, what we really measured in the experiment is not A1, but the longitudinal asymmetry in the beam direction. And there's a small contribution from G2 if we want to transform the longitudinal asymmetry into A1. But that's not a problem because there's a plan to measure G2 with a transverse polarized ion beam. So G2 will be measured, and we can go from the measured asymmetry to A1 without adding uncertainty from this correction. Because it's a collider, there's no dilution of the target, so there's no issue there. I assume that the contamination from particle misidentification would be negligible, and also because we measure an asymmetry, all the absolute factor coming from detector trigger efficiency and the beam current, their uncertainty will not contribute, will be suppressed in the asymmetry. So with those assumptions, and assuming in addition that 60% of the systematic will be point-to-point uncorrelated, except for the low X error, and I'm assuming 60% here simply because it's what we got for the G1 DVCS experiment. So I assume it would be similar for EIC. So assuming those 60%, the data from EIC may look like this. Here, the central error bar shows the statistical precision, and the outside error bar is the point-to-point uncorrelated uncertainty, systematic uncertainty. Finally, the band, the pink band, shows the point-to-point correlated uncertainty. So this may look pretty bad here, but if you look at the Q-square value here, please notice that we will stop the extraction at between 10 and 20 GeV squared. So the systematic, the point-to-point correlated uncertainty is still well under control. So using those pseudo data, we can fit them using the same procedure as for the EG1 DVCS. And if we do that, we obtain an alpha S with about 3% precision on it. If we add another data point, we improve the precision a little bit, but we worsen the accuracy a lot. So it's not worth including more point than those the point in this range. So comparing this expected result with the EG1 DVCS, you can see there's some significant improvement, and also comparing to the current PDG world data, you can see that what we can get without being too pushy at the UIC is reasonable compared to the current data that are given by the PDG. So in conclusion, under reasonable assumption, the EIC can yield an accurate measurement of moderate precision. Here I assume statistics similar to a typical class experiment aiming at measuring inclusive spin structure function. So that's rather conservative in terms of statistics. If we increase the statistic by a factor 10, then we would get an alpha S with a precision of about 2%. And then if we're able to tag the spectator neutron when we take the deuterium data, then we can reduce this uncertainty to 1.6%, which make it a competitive measurement. So to summarize, I discussed the extraction of alpha S from the Bjorken sum. We extracted it from an experiment at GLab at 6 GeV called EG1 DVCS, and that yield an alpha S of about 0.112 with a 5.5% uncertainty on it. The central value is on the low side, but it's still agreeing with the current PDG average. This can be improved with the future experiment with the upgrade of GLab to 12 GeV. We expect a precision similar to EG1 DVCS, but with a better accuracy and a greater Q-square reach. We can also apply the same technique for EIC, and I made an exploratory estimate that suggests that an accurate measurement of acceptable precision is possible. So I think it's worth investigating this possibility more in depth. And there's a few things I have not discussed. We can improve the extraction from the Bjorken sum by including lower Q-square point. One way to do that would be to include higher twist correction to the extraction. And another possibility is to use non-perturbative model of alpha S or of G1 to help. And for example, we did that using the ADS QCD model and match its prediction for alpha S to the prediction of PQCD in their overlap domain. And this exercise have yield a competitive estimate of alpha S. So here is what we obtained. I'm showing it in terms of lambda QCD. And that's the value of lambda QCD obtained at each order of the perturbative series. And you can see that when we go to a high enough order, we're converging nicely to the PDG average, and also the overall uncertainty on the extraction is the same as the world average as it was in 2015. So we may argue that this method is model dependent, but ADS QCD is actually a model closely related to QCD, and it's not obvious to me that this model dependence is worse than some of the assumptions that are made by using PQCD-based or QCD-based technique. So I think it's worth considering this type of extraction, especially with models such as ADS QCD, which have yielded many very good prediction concerning QCD. Finally, I didn't talk about alpha S that we can extract from the Q-square evolution of G1 or of the proton moment, but evidently such possibility will be available if we take the data for the Bjorken sum. And that's all I have. Thank you.
Thank you very much for this interesting talk. Do we have questions? Questions from here, from the room? Okay, I don't see any question. Okay, so then thank you very much again.
No, sorry, Julia, I had questions.
Sorry, David, I didn't see you.
No, I didn't raise them. I didn't raise the hand because I thought there were. Okay, anyway.
Go ahead, please.
Thank you. That's very interesting, Alexandre. That's something that had not been incorporated so far into the world average. Let me see, your analysis is NNLO, or what is the accuracy, perturbative accuracy of the current extraction that you have?
So we actually went to alpha to the fourth. That's the form we used to fit the data.
Okay, so the perturbative accuracy is NNLO or N3LO. So this is in principle, I mean, the PDG, I mean, Julia can correct, Joy can correct me, but this is in principle in terms of theoretical accuracy, this would pass the criteria to be incorporated into the world average. Of course, I mean, it will not be super constraining because it has a 6% uncertainty, but still, I think we should incorporate this into the PDF fits category, shouldn't we?
Yes, I think one can, sorry, yes. I think so. One can include, it will not, it has a large uncertainty, so it will not have an impact, but one could, yes.
Can you show again the categories from the PDG where your value is, Alexandre?
Oh,
please.
Yes, I have it with the latest one here.
Yes,
so
this one here.
Yeah.
Okay, this is the current, this is your published work from
2014.
14, okay.
2014.
Good. And yes, what about the, I mean, but I mean, of course, I didn't, I mean, I couldn't look in detail into your assessment of the expected uncertainties, but you look pretty conservative. You did a very detailed study of many systematic effects, both experimental and so on.
Right.
And theoretical, and it looked conservative. I think improvements are possible. Is there anybody planning to do a JLab 12 analysis of the class data to try to do this extraction? You have all the framework, don't you, to do the fit?
We do, and I'm sure we will do it. And I also agree with you that basically this extraction in 2014 that was the first we did, and that was exploratory. Certainly we would repeat it now. We certainly could reduce the error. So if there is interest on that, we can look at repeating the analysis. Just the better PDF to correct, for example, for the higher twist would reduce a little bit the error, although, and maybe permit to go to a lower Q-square to make the extraction. So. Certainly, if there's some interest, we can revisit the analysis and probably improve the uncertainty. I
think yes, the more observables we add, independent observables we add, the better. So I would welcome this. Thank you.
Very good, thank you.
Okay, maybe we move now to the next talk.
Stan Brodsky has a question, Julie, I think.
Sorry.
I was suggesting maybe if you have the curve, maybe to show the total curve from the ADS QCD, how it interpolates between the low Q squared and the high Q squared.
Oh, I didn't put it in the talk. I'm sorry. I'm only showing the final result here, where we can see how the alpha S from the matching is obtained at first order and then second order.
I can't resist to add that it shows the running coupling at virtually all the way from Q squared equals 0 out to Q squared equals infinity with a matching scale between non-perturbative and perturbative. And there's only one parameter in the non-perturbative, and that comes from the complete regifit to the whole meson, baryon, and tetraquark spectroscopy of hadrons. So actually, we have a really much more comprehensive understanding of the running coupling QCD from low scales to high scales. And that's thanks from our work with you.
Right, and I didn't have time to get into detail about this extraction, but the heart of the method is to match this single parameter that you mentioned that come from rigid trajectory to lambda QCD by matching the prediction from ADS QCD to PQCD. And when we do that, that's what we obtain. And as I said, I'm impressed by the result of the ADS QCD framework. They have a lot of impressive prediction. And that's why I think, although it's a model-dependent extraction, it's something that should be investigated or considered a little more.
And so what one has is really, in fact, a complete model with color confinement all the way at Q²=0, all the way to the perturbative domain. So I think it's the first time one sees this matching between non-perturbative and perturbative physics in a very elegant way, consistent with virtually every test one can perform. So I thank you for your talk.
Thank you, Stan.
Okay, thank you very much then again, Alexander. Can you stop sharing?
Thanks to the organizers for having me here with a slightly off-topic contribution. I hope that I can relate this to AlphaS sufficiently that you'll still find it interesting. I'm sorry for people in Trento that I couldn't travel to the ECT Star venue this time. I know it's annoying to listen to online speakers if you're in a conference room, but I'm afraid there was no other option this time. I do hope to return to Trento in the future.
Excuse me, there is a kind of a box in front of your slides, which
is it
okay.
this?
Yes, thank you. It's gone. Okay.
Yeah, sorry about that. So I'll talk you through an extraction of the bottom quark mass from Higgs precision measurements. The results on the archive since a couple of months, since October. And it's work by a number of experimentalists with some theory reinforcements. We managed to get Germán Rodrigo, André Wang, and Michael Spira to help us work out the theory aspects of this. So I'll start with AlphaS. So of course we know that the scale evolution of the strong coupling has been very well tested over a very broad range of energy scales. So we have precise is a relative term, but we have good determinations up to 4 TeV. I show some atlas plots here. And we come from a much lower scale, of course, so this plot really collects a lot of measurements in different processes with different theory calculations. And I think the merit of the plot is, in fact, that it does collect all that information in a single interpretation, so that we can see subtle deviations from what one might expect. Now, a simplified picture of what that looks like is I've drawn the line with some ad hoc shifts due to a massive colored particle that sits at about a TeV and starts deviating the evolution because right, there is a new colored object in the game and evolution is affected. Now that has been done by several authors. I listed 2. I don't think this is an exhaustive list, but I think that is a very interesting game to play, and I hope we can do it with masses as well. So quark masses, we have a lot less evidence that the scale evolution is as QCD predicts, but there is some. We of course do expect masses to run as well. The charm quark, the plot I have here is from Hera. The low energy MC is the red dots, and the black points are clearly lower. So we see some evidence here that indeed there is a scale evolution. The bottom quark mass is what I'm talking about today. It has been tested by the lab experiments in SLD. There are many papers on this. I recommend this review by Stefan Klut, but I will go through these in more detail. And attempts have been made to do the same thing for the top quark mass. And in fact, thinking about the top quark mass measurement is what triggered this study. We were at a little workshop in DAISY, and we started thinking about how one could measure the top quark mass and its evolution. And then this old idea was dusted off and put into practice. So of course we have Higgs measurements, you are very well aware of that. And since 2012, we have quite a few bits of information, right? We saw the Higgs boson in ZZ decays, photon decays with a bit of a contribution for WW. Evidence for tau decays came in 2015, bottom decay in 2018. We also saw VH associated production, TTH production. That was a good year. 2020, we start to see some evidence for Higgs to tau, evidence for L plus L minus in a photon in 2021. So gradually we're filling that plot on the right with increasingly precise data. So, and I'll show you today that these measurements open a new window on the bottom quark mass. It's maybe not the most obvious application of these data, but it can be done. And it's surprisingly precise. So we're starting to fill a page in the PDG for Higgs boson properties. And as I said, a lot of it is at 10, 20% precision, but precision is increasing very rapidly. And these Higgs decays are interesting to study the bottom quark mass for a number of reasons. A lot of them have been known since a very long time. We expect, of course, a quadratic dependence on the bottom quark mass, which makes it a very sensitive measurement with relatively poor precision. You can still get quite a precise bottom quark mass measurement out. It's an electroweak decay, so the rate is decoupled at leading order from the strong coupling alpha S, and this is a feature that is very useful. In fact, in the attempts to measure the top quark running, that is one of the big problems to disentangle the evolution of alpha S and the top quark. It helps, of course, that very precise predictions are available for the decay process. And a particularly elegant feature, I think, is that in this process, the Higgs decay, the scale is MH. I don't think anyone will argue it, that it should be a very different scale. We, in our paper as an illustration, we compare the QCD series. When you set mu to MH, you get a nicely convergent series that I've shown in the little inset there. If I take another choice for the scale, for the central scale, say the bottom quark mass itself, I get much poorer convergence. So we can really see from the series themselves that the natural scale is MH. That's where things are happening, and that's the scale that we should set in the calculation. Now we have to choose a mass sensitive observable, and we chose to pick a ratio. And that is because the LHC is much better at measuring ratios of production or decay rates than it is at determining absolute rates. So in practice, the Atlas and CMAS collaboration often publish all production processes normalized to gluon fusion, and all decay rates normalized to Higgs to ZZ. And that way, a lot of the systematics cancel, and that helps us control the precision. So the standard model prediction for the ratio of bottom quark width over Z width is 22.0 plus or minus 0.5. That's a small uncertainty. This is the value quoted in the yellow report. We have obtained our own value, which is 21.8, compatible within the uncertainty that we can assign to this. And we've added an additional uncertainty because the Higgs mass itself is not known infinitely precisely, and that changes, especially the ZZ with a bit more than is captured in this uncertainty. The experimental measurement is, of course, way behind the theory still, approximately 20 to 30%. So we use two measurements, one by Atlas, full run 2 results, but this is a preliminary result. It's 0.87 plus or minus, well, plus 0.28 and minus 0.21. The CMS result we use is a partial run 2 result with only 35 inverse femtobarn. It's slightly less precise, but very compatible with the Atlas result. Now, since we started this, Atlas has updated its results. The value shifts quite a bit to 0.75. We're anxiously awaiting, of course, a combined run 2 result from Atlas and CMS. So with this, we can calculate the expected observable as a function of the bottom quark mass. We use prophecy 4F for the ZZ decay and H decay for Higgs to BB bar. Those are state-of-the-art tools, and we could essentially use them out of the box. We did request a slight change to H decay so that we can provide the bottom quark mass at the scale of MH directly. So that is now publicly available in version 6.6.1. We combine both measurements with Convino. I won't go into the details. And that yields the first measurement of the bottom quark mass at the MH. It's 2.6 plus 0.36 minus 0.30. If you evolve that back to MB, you get 2.79, vice versa. If you evolve the PDG world average to MH, you get 2.79, so that's compatible within the uncertainty. The theory uncertainty, we've gone into a bit of detail to understand this because we like this method because of its theory properties, and indeed the theory uncertainty comes out very small, 60 MeV, completely negligible currently. And we've been quite generous, I think. We've included scale variations and an estimate of the next leading order electroweak corrections. That gives us 0.3 to 0.5% on the ratio that we use as input. The parametric uncertainty from alpha S we take as plus or minus 0.01. That gives us 0.2%. Again, as we saw before, the prediction is relatively insensitive to alpha S. And because we use the MS bar mass directly at the scale of MH, we don't suffer from the alpha S contribution in the evolution. And we have a parametric uncertainty on the Higgs boson mass. The measurements are a bit more precise than this 240 MeV, but they're not quite on top of each other. So we've decided to be conservative, and that gives us the largest contribution to the uncertainty today. Of course, we expect this to come down in the future. So with all this, we can now go back, make a plot, put MB from the PDG world average that is based on low energy measurements as a green star. That's the lowest end of the plot. We put the LEP and SLD measurements with blue markers at MZ. and we have the two new results from ATLAS and CMS and their combination. So the average is the red star on the right of the plots. That is the main result of this work. Now, these measurements are independent. They make different assumptions. So we can now test the evolution that QCD predicts, which is the solid line with the gray band, and see how significant the evolution is. I want to remark that what we have today is not very precise, but it is already as precise as the combination of lab measurements. And I will show later that we have a lot of room for improvement here. One thing I should explain in a bit more detail, especially at this workshop, is what we did for the evolution. Of course, it has an uncertainty due to the uncertainty on the reference low energy mass itself. There we took the PDG uncertainty. We assign an uncertainty on alpha S, and that affects, of course, the value that we end up with at MBMH. The 0.001 from the PDG uncertainty on alpha S of MZ is the darker band, but we add an additional uncertainty of 0.004, which aims to capture the uncertainty in the actual measurements at MZ and MH. So we don't want to assume that alpha S runs as QCD prescribes if we're going to test that the mass runs as prescribed, because of course a new colored state would affect both. We have included an assessment of the missing higher orders, but that's negligible at this precision. So now we can do a test. You can do that in several ways. We've chosen a simple one that is based on the CMS paper on the running top mass. We interpolate smoothly between a no running scenario, which you get if you put X to 0 in this formula, and the SM prediction, standard model prediction for X equal to 1. And then we fit in two parameters, MB, the reference bottom quark mass. I'm sorry for the uncertainty that got a bit garbled, but you find we get the PDG value and its uncertainty back, because that value is so precise that the high scale measurement don't really pull that away from the reference value. And we find an X value of 1.08 plus or minus 0.15 plus or minus 0.05. That is compatible with the standard model prediction of 1, of course, and it's incompatible with X equals 0 by about 7 times the uncertainty. So of course we find that the RG scale evolution is confirmed, and we can rule out the no running scenario even more precisely than we could. With LEP only, we would have gotten 4 point something sigma. So there was good evidence that things behaved as predicted by QCD, but we have strengthened this with the new measurement. Now, how much better can we do in the future? I dug up a number of projections for Higgs precision measurements. The yellow report gives us a high Lumi LHC expectation for this ratio of 4.4%. That's the S2 scenario for insiders. It's aggressive but reasonable. There is some improvements in systematics on top of improvements in the statistics and some improvements in theory, but I think that is an achievable target. If you translate that into a bottom quark mass, you get 60 MeV. That's already getting to 2% precision, 2 and a bit. Now, a Higgs factory can, of course, do better still. There aren't projections in the published literature for this ratio that we use, but Yunping Tian, who did the fits that are part of the European strategy, briefing book gave me some numbers that come from the same fits. So this is just a reformatting of the basis in which it's presented, essentially. With ILC 250, take that as a proxy for any Higgs factory. We get 0.86% precision on the ratio of bottom to W. At the Higgs factory, it is preferable to use the W as a reference because the statistics is higher. That would translate into a 12 MeV experimental uncertainty. And if we add the 500 GeV program, the ILC can make a better measurement, halving the precision, and that would translate into 6 MeV. So then we're at the 2 per middle level on a bottom quark mass measurement at MH. Now, of course, at that precision, we have to worry about theory again. The parametric uncertainties due to MH should come down very, very rapidly. And we also expect, of course, Higgs factory to add to alpha S. So I'm fairly confident that those can be brought down to a comparable level of the experimental uncertainties. At this point, we don't know what will happen to the theory uncertainty, in particular from electroweak corrections. That, I think, needs some specific study before we make a concrete and credible projection of uncertainties in this range of precision. But it's clear, I think, that the high Lumi LHC and the ILC, or another Higgs factory if you prefer, have the potential to improve the experimental precision, and theory is already very good, and hopefully it can keep on matching the experimental progress at this point. Now, we also did a little study as to what we can do at other scales other than MH. One thing that would be interesting is to extend the reach, but that turns out to be rather difficult. We've looked at measuring MB at a scale of 250 from the Higgs factory data, but really the mass sensitivity decreases rapidly, and it becomes very hard to do a measurement like the lab experiments did at such a high scale. At the Z-pole itself, we can access the MBMZ with either data taken at a center of mass energy equal to the Z mass, giga Z or tera Z in the jargon, or we can use radiative return events at a higher energy. So I've added those points to this graph, and of course we don't expect a dramatic improvement. We can improve considerably over the lab and SLD results. Now, the small print for this measurement is of course quite important. We have to assume only one thing, but it is one of the big questions in high energy physics at the moment. So I wanted to spell that out rather clearly. We must assume, of course, that the standard model has a negligible impact on the observable that we're measuring. Now, if you think through some scenarios that could happen, the measurement and the way it's presented in this ratio is actually quite robust. You can add an invisible decay with very little impact on the ratio because it cancels to first order. Other assumptions like the Higgs boson production cross sections can be tested to good precision as we get the high Lumi LHC data or the Higgs factory data. We'll see things starting to go askew elsewhere before it affects this measurement in a significant way. Now, there's one exception, of course, if the bottom quark Yukawa coupling is non-standard and none of the other Higgs couplings show any sign, then of course we would find that this mass measurement is biased. So strictly, the results I've shown are valid only for a standard model bottom quark Yukawa coupling. Now that is true to some extent for all these mass extractions, but this is a particularly delicate assumption to make. So I wanted to make it very clear. So in summary, we can now present a new measurement of the bottom quark mass at the scale of the Higgs boson mass. You've seen the value. I've explained the caveat. We think this is a nice method because of the theory properties and the very good prospects for improving in the future. Now, we hope that new and better high energy measurements can be used to turn this evidence for evolution into precision studies of the scale evolution predicted by QCD. And a project that we have in the back of our minds, but haven't really flashed out, is to do a joint fit of the scale evolution of alpha S and the bottom quark mass, maybe also the charm quark mass, to derive bounds on massive colored objects. We're not quite sure what the impact could be, but I hope I've convinced you that the bottom quark mass tests of the evolution can become of similar precision to the evidence for alpha S evolution, and then it's interesting, I think, to combine both pieces of information. Thank you very much for your attention, and let me know if there are any questions.
Wonderful. Thank you very much for this very interesting talk. Do we have questions? I see a hand by David. Stan.
Stan, is your hand before, or is it a question to this talk?
Yes, I just can't resist making a remark about scale setting. You can eliminate the renormalization scale ambiguity for the running mass, just like you can do for the running coupling. This is just like in QED. In QED, there's never any renormalization scale ambiguity. You can work an MS bar, any scheme you want, and that you can determine the running coupling by simply, for the case of the running coupling of QED or QCD, you determine the beta terms, that's the vacuum polarization in QED. And then by identifying the beta terms, you sum them, and that gives you the running coupling at any scale. Similarly, you can identify the gamma terms, which go into the renormalization equation for group equation for the running mass, and you identify the gamma terms order by order, you resum them, and then you just use the standard equation for the running mass. And that there is no scale ambiguity. The only ambiguity is how far you go out in perturbation theory. And each order in the theory, just like in QED, has a different renormalization scale. This is the Gell-Mann-Low procedure. It's exactly what's used in QED. And if we have a grand unified theory, you can hardly use a different procedure for setting renormalization scales in QCD than you could in electroweak theory than you do in QED. And also there's even a theorem that you can actually make sure that every formula that you use in non-abelian theory agrees with the abelian theory in the NC goes to zero limit. So actually there really is no ambiguity in setting renormalization scales. You never have to guess. Of course, in your case, every scale will be surely order the Higgs mass, so that won't be a big error. But there's no reason to have an uncertainty at all in the renormalization scale of the running coupling MB at any scale. And in any scheme, it doesn't matter what scheme you use, you'll always get the same physical answers. So I just couldn't resist saying this because it seems there's so much confusion about this. It's astonishing, actually. I think I always joke, if we meet someone from another planet, they all say, of course, you just determine the number.
Okay, Stan, maybe, do you have a question? Or because I would have a question to this presentation. So,
the question is, why don't we use this?
I do have a question too, maybe.
Okay, so David, do you would like to go ahead?
Yes, can you go, please, Marcel, to slide 16? If we run FCC with the Z at the Z pole with 10 to the 12 Z's, we will get uncertainties reduced by a factor of 300 compared to lab. So then you can go from tiny statistical uncertainties. Now you can run to the close by Higgs scale, or you can go down to MB scale. Have you done this exercise? So assume you have a value at the Z pole with 300 times smaller uncertainties, and can you run it down to MB and up to M Higgs and see what you get as propagated uncertainties?
So yeah, so the square in this plot, the little red square at the Z mass, that is our estimate of how well you can repeat the lab measurements where you use 3 jet rates to get MB at MZ. But we've assumed giga Z, which is a factor of 1,000 less Z bosons than in tera Z. And we've been a bit more conservative on the limitations that come from systematics. So we've assumed a factor 2 improvement in the theory uncertainty, which is reasonable given that an NNLO calculation should be available by the time we do this measurement. Maybe it is a bit conservative. And things like hadronization uncertainties, we've also scaled by a factor 1/2. Now, I find it very hard to make solid arguments for these predictions, but it seems likely that those type of systematics will limit progress well before we reach the statistical potential. But yeah, I agree. The experimental statistical precision can be anything you want, essentially, once we run giga Z or tera Z, and even the radiative return events are quite a good source of Z bosons.
Have a question here from Stefan?
Yeah, hello. Well, we talked about this earlier. So it turns out you can probably measure the MB at MZ using the electroweak precision observables at a future facility. So I tried that. I have a preprint for that.
Yes.
And if you do this with FCC-EE expected uncertainty for this electroweak observables, you get something like a 5% measurement out, which is, I guess, corresponds to 100 to 150 MeV error. But that would be like completely without hadronization uncertainties and stuff like this. It's pure electroweak plus QCD. So that could be interesting.
Yes, I agree. That right. I read your paper, of course, and the current level of electroweak precision measurements, we don't really add all that much to the 3 jet measurements, right? But you say that if you project this to say the FCC prospects for electroweak precision observables, you get which precision?
5%.
Okay. Yeah, that's definitely better than the number we have here.
We have another question. Okay, we have another question.
Yeah, hello. Concerning exactly this slide, maybe that would be an interesting scenario also to have either radiative return or dedicated runs even below that peak, and having some additional point around 50 or maybe even smaller energy, it could be also beneficial, and to my opinion. But have you considered such an opportunity?
No, we haven't really thought about that. Yes, I agree. The slope of the curve already suggests that a measurement there would be interesting. Right. One thing that happens at very high energy is that the curve flattens out. So there isn't so much to be learned about the difference in the mass between the Z pole and 250, for instance. Now, the interest of those high energy points is that a more massive state could lead to a bigger change in the evolution, maybe. Yeah, no, it's an interesting comment. We really haven't thought about it, but there must be ways to populate values in between MBMB and MBMZ. It's a nice subject for further work, but I don't have a good idea right now how that could be done, but yeah, it would be interesting to look into that.
It could either be done using Andri's proposal and colleagues' proposal of running future facility for a couple of days below the Z mass, which would get enormous amounts of data, certainly if it's a circular collider. And other possibility is similar to what you say, to use radiative return, B-jet production below the Z mass. So if you accumulate giga Z, you get radiative return events with effective center of mass below the Z. So, and if you take them with BB bar production and get enough of them, you can try a jet production-based measurement of MB at M square root of S prime or something like that.
It would still be a 3-jet rate measurement, but
yes,
but you just shift the center of mass energy.
But since if you have at giga Z infinite number of Z's, you get also a very large number of radiative return events.
Yeah, that makes sense.
And it completely copulates the range in square root of S between the very low ones and the Z peak.
Very good, thanks.
Maybe I can also ask a question. I mean, to some extent, this is really a measurement of the Yukawa coupling more than the mass, no? Of course,
it
in the
is.
model,
Yeah, you have to assume the relation between the two that exists to get a mass out. Now, there's always a relation that you have to assume to get any mass out of any measurement.
No,
but I agree that right, this is new and unexplored territory to some extent. So it is a bit of a delicate assumption to make.
Wouldn't it make more sense to interpret this as a measurement of the Yukawa and see how much one can constrain EFT effects that would change the Yukawa given other measurements of the bottom mass? Or
yeah, right, but I think that that is done. It's an alternative interpretation of the same data.
Mm-hmm.
Of course, if the results start to deviate from the standard model, we should look at that projected in as many different ways as we can. But as the alpha S plot is useful to collect all the different types of data, and this is an alternative way of looking at the same data that I think gives another view, another way of spotting maybe slight inconsistency.
Okay. And maybe I missed in terms of theory predictions, what is the accuracy exactly that you have here? So you have massive matrix elements at up to an NNLO, including top loops and is that the case?
Yeah, let me see. So the QCD prediction is n4th LO, but it's massive, fully massive only up to NLO or NNLO, I don't remember.
Okay.
I can forward these questions to my theory colleagues.
No, it's fine. It's fine. I can.
We can answer on Mattermost or.
Okay. Let's see. Sorry if there are other questions. Okay, Simone, please.
Yeah, I have a curiosity about what you just suggested, Julia. So I don't know for the question whether it's for you or for myself. In terms of reinterpret this as a measurement of the Yukawa, but should I be worried? I mean, is the dependence of there will be a kinematic dependence also, which is really in the matrix element. Should I try and disentangle the two, or does it? Or maybe this is negligible at this stage.
But I think here the dominant dependence comes from the Yukawa, but that's why I was also asking exactly what are the matrix elements. In principle, there are the two, and one could disentangle. One could take the Yukawa as MB at M Higgs and the other masses, even MS bar, no? It could be disentangled, I think.
It was just a curiosity.
Yeah, I've had this question before. I don't think we've worked out to which extent that would work, but I think it's an interesting direction, and we should pick it up.
Are there other questions? Okay, I don't see any. So let's thank Marcel again. And we have some time for discussions now. I don't know how we want to organize the discussion today. There were some points left
I'm sharing the your
yes,
categories. Maybe we can discuss. Maybe we can discuss things that were presented today. I like to. At the end, I'm a bit. I'm sorry to be provocative. I'm a bit disappointed because the E plus and minus shapes and jets, we are not yet. We are not making yet progress to reduce all this spread. So I'd like to understand from the experts what can we say something? Can we improve this in any way? Do we have any? Have we identified any interesting path towards reducing the individual uncertainties and also the spread on these results? I mean, do we agree on what is the path to improve this in terms of analytical non-perturbative corrections or Monte Carlo hadronization and parton showers development and so on and so forth? Can we conclude something for the next 10 years? Because that's something we should address in the white paper. Anybody want to comment?
Yes, in just a second.
No, I think what was presented today was a breakthrough, actually. So the possibility of computing the non-perturbative effects in a three-jet region was never done before. It makes a difference. It seems to be pointing in the right direction. Of course, it just started, right? So we have to see, with fits using this information whether things improve. But something new has happened. I mean, there's no doubt about it.
And but nobody tried to do any phenomenological analysis with this.
I mean, these publications are from the end of last year and beginning of this year, so it's to be patient a little bit. We will do it, right? It's not very recent. This is very recent stuff.
But can you at least guesstimate what the improvement could be?
The estimate was given in the talks by Pierre, right? Depending upon the interpolation, there was a displacement of the central value of three estimates. And according to what we find, the most aggressive one, the most aggressive interpolation that he was showing would lead to a value which is much more consistent with the world average. So it's all in today's talks, actually. So if you want to have an idea of which way we are going, right? And then, of course, serious work, I mean, not just indication, but serious work is ahead of us, I think.
And not just the central value, what about the sign uncertainty? Do we have can you estimate this?
I mean, if I say, look, I mean, the whole thing has to be done, right? So one important thing is that already with analytic estimate, probably this discrepancy is going to be become a lot less severe or disappear. Then we will see about how consistent the whole picture will be. But this you need to fit several shape variables using these new assumptions on the non-perturbative corrections and see if you can really reduce the error. But I cannot tell you just out of my head. It's just new stuff, as I said. Right? So.
And this will, sorry for the naive questions, maybe, will this progress impact both the shapes as well as the three jet rates and ratios of 2 to 3? Maybe Julia or Pierre can comment on this. All these improvements will impact both type of observables, event shapes as well as jet rates, or?
I think also jet rates, although it hasn't been done. Jet rates are talking about the plus and minus. Huh? So I think also in jet rates, this thing can be applied. So it hasn't been done yet, right? But
because this category contains both, as you see. I mean, you have C, T parameters and so on, but you have also jet rates.
Yeah.
In a plus and minus. Maybe yes. Julia wants to comment, or Pierre. I don't know.
So yeah, I mean, like in this category, most of the at least the fits with smaller uncertainty are dominated by non-perturbative corrections. So we're in a position where perturbative calculations in this observables are at a stage that further improvement will be not directly necessary with lab data list. And so improving requires understanding hadronization to an extent which is very complicated. Concerning jet rates, there are some people studying. These are more complex observables, and non-perturbative corrections that are more complicated scaling. There are some people studying them, but this might be done at some point in the future, but it's hard to predict. An interesting other direction is what Simone presented, maybe try and avoid the hadronization problem altogether, or understand whether that's possible at all using LEP energies or FCC. That's, I think, an intriguing direction. Perhaps also understand how to exploit this at the LHC to its full potential.
Another naive question. I guess that B factories, E plus and minus results cannot be used at all. Is too low scale for this type of analysis, or?
It's very non-perturbative. Non-perturbative corrections are very large, so these problems become way more prominent there.
Yes, just a second.
Just concerning the progress in theory, I already said before that tremendous work was done by our theoretician colleagues, but there are still some things that could be in principle improved. I don't believe there will be, I would say, huge impact, but from a point of view of completeness, it would be nice, for instance, to have full NNLO predictions with massive quarks. As far as I understand, it's not very interesting right now for theory community, but it would be nice to have.
You mean like C to BB? That's what yeah. Yes.
Yeah, I agree. That would also be on my shopping list. And one reason is what we just heard in the last talk, that the determination of MB from Z decays to BB jet, of course, is limited by the NLO calculation that's available for it, which so it limits theory uncertainty. With NNLO, then that theory uncertainty that's there from scale variation will likely halve. So that could help a lot.
Okay.
Any more
Yes,
comments?
There is a comment
the,
here. Just a
plus
second,
and minus?
David,
Sure.
just a second.
Yeah, on the program that Paolo was mentioning with calculating non-perturbative corrections in the free jet region, of course, this is just the beginning, but can we think about doing that somehow in numerical codes so that people can apply this to, the observable of choice, maybe together with calculating the fixed order prediction or something like that? Or because otherwise it needs a dedicated calculation for every observable, and then of course it will take a long time until a collection of results is there that makes an impact.
I mean, these calculations are not difficult. I mean, you can do them numerically, analytically, and even studying a single observable doesn't take long. So it's not, of course, there are tricky observables, but for most of them, I don't think this is a problem.
I see one hand. Sandy, would you like to add something?
Yeah, so in the non-perturbative domain, there's a lot of new work on it that comes from light frontallography, ADS-QCD, which builds in confinement. It has the what's called a cap of the 4 zeta squared term, which it immediately gives you all the confinement between the colored particles. So it's very important, I think, for the non-perturbative contributions to jet physics and so on, because now one has a theory actually which combines QCD perturbative and the non-perturbative aspects of QCD, including color confinement, which is highly non-trivial. It's all analytic, and there's many papers now that are coming out of this very highly cited work, because it's, as I said previously, it also gives the complete Reggie spectrum of all the hadrons, the mesons, the baryons, the tetraquarks for light and heavy quarks. So it's really, I think, a profound advance that people should be looking at. And also, I can't resist also adding the fact that you can eliminate the renormalization scale ambiguities in these observables that are shown in the slide. And that's the same way you do in QED. It's the Gelman-Low procedure. You just sum up all the beta terms for running coupling or the gamma terms for the running mass. And it's rigorous. First principles base every renormalization group equation. The results are scheme independent. This is the BLM, Brodsky-Lepage-McKenzie procedure. It's now called the PMC procedure, principle of maximum conformality, because it shows how you do it at every order. And it is really totally rigorous and systematic. So people should really be looking at this. And it's, I think there's a mythology that's grown up over the years that people think that you can't set the renormalization scale. But once you choose a scheme, the scales are not ambiguous. And when you relate any observable to any other observable, the answer is scheme independent. Not only that, you eliminate what's called the renormalon divergences. There's no n factorial divergences in the series anymore. But there's a huge literature on the PMC. And for example, particularly in China, the Jingang Wu's group and so on has done many different observables with the renormalization scale eliminated using the PMC. So anyway, I urge people to look at this or challenge. I mean, I know, in fact, people think, no, it can't be possible because over all the years we haven't set the renormalization scale. We've just guessed it. But that's actually not really right. You really can do it rigorously from first principles. Order by order by order, you can set the renormalization scale.
Thank you, Stan. We have another comment here from the audience.
Thanks. So I want to go back to what David was asking earlier. So a parallel direction of work that can impact this category is improving, quote unquote, improving hadronization models in Monte Carlo, right? This is a complex question, but there are some indications that the key point is improving the perturbative accuracy of these tools. So that the hadronization model actually is something that modifies the kinematics of the event only locally. That is what physically should do. So this is a direction to push anyway, independently of this. And having better Monte Carlos and showers would eventually lead to better tunes that might impact this category directly. This is more complex and it's a broader question, but this is something to keep an eye on in this respect as well.
Yes, can you tell us what is the current state of the art regarding with the log accuracy of the Parton showers? This one family, did it reach NNLL accuracy or?
No. Next to leading log is almost completely understood, but we're very far from next to leading log. It's a very open problem. Yeah.
Okay, so let's assume we have next to leading log fully understood. Then what we have to redo? Can this be easily implemented into Pythia, for example, or other Parton showers, and then do a refitting of all hadronization data? Because part of the evolution will absorb some of the not purely hadronization models.
Right. So yeah,
can this be done?
So the algorithms themselves are simple enough that they can be implemented anywhere, basically. But there are also the questions of matching to higher order for the hard scattering. And that question of matching can easily break accuracy. So that's also an open question that people are starting to address now. So I think in the next 5 years or so, we'll know much more to actually build more accurate generators. It's definitely an interesting and an important point.
So ideally, so what you're saying ideally is that by improving the log accuracy of the Parton showers, and refitting the parton fragmentation into hadrons from clean data, from E plus minus data, we will have hopefully a convergence between analytical results and observables in this category that have been corrected for with parton with Monte Carlos. Is that the?
Yeah, it goes in that direction. It won't be a complete match. I mean, analytical calculations will be always a step ahead. Also because these tunes are done with very complex exclusive observables. Very often one needs to account for hadron masses precisely and so on. So it won't be a solved problem, but it goes in that direction. So building better, more perceptively accurate Monte Carlos, both in the shower and hard scattering calculation, certainly should move us in the direction of having better fits of hadronization models.
Very good. And then we have the data. Stefan Klut, can you redo, if you have a new parton shower, can you redo these results and these corrections? Is it easily with all lab data, or?
That would be possible, because that would involve doing another fit on published distributions of event shape observables. And that has been done many times. Several of the analyses are shown in the table. For example, the EEC analysis, Cardos and company, that was done on published EEC data dating back decades, or the work by Verbitsky, by Andri, also was done on published results for two-jet distribution and so on and so on. So if that becomes available, a reanalysis is possible without having to go back to the actual data and reproduce distributions.
Good. So from Paolo's comments, if I want to be optimistic, I understand that these analytical event shapes parameters will approach to the current world average with reduced uncertainties, and at the same time, by implementing improve NLL parton showers, those results also will converge with reduced uncertainty. So hopefully this category will show a smaller spread in a few years from now. If that's, is that something too optimistic, or? Of course, we have the analysis has to be done. You cannot forecast, but that's the idea, I guess. Or am I missing something?
So I mean, one can only be optimistic or pessimistic, but the message is that there is something new now. So we can hope that there will be also improvements will follow. Right?
Very good. Okay.
Okay. So yes,
shall we
David?
go, Julia, the two other categories that were discussed today rapidly?
Yeah, briefly. It's 7 o'clock, and we have a bit of a tight schedule.
Yes.
So
okay. I mean, I don't know. I mean, I don't know if Vicent wants to add anything about these QQ bound states, and whether, I mean, we heard from Alexandre, we have this interesting Yorkian sum rule for spin PDFs that will add some new point here. So I don't know if we want to discuss something beyond what was discussed already. That's most the question than anything else. Do we need to go back to this, or everything is covered already?
Well, concerning this QQ bar bound states, I'm glad that the determination appears on the PDG, but that was not the aim of the article. The article aim was to fit for bottom masses and to show why you cannot successfully fit for alpha strong. That's why we made the other paper with Diogo Boito, just to make sure that you can do it much better just by losing the dependence on the unwanted parameter, right?
okay.
One can probably do something similar with the bottomonium masses. I'm not saying that, but the thing we started with was the sample moments.
Mm-hmm. Yes, of course. I mean, once you deal with heavy quarks, masses and alphas are extremely coupled. So uncertainties on one and going to the other, and the other way around. So usually you extract both. That's why also we wanted to have analysis like the one from Marcel on the bottom, because this shows the degree of coupling of both parameters. Then assume that we have from somewhere, lattice or somewhere else, we have a very accurate extraction of the masses of the bottom and the charm quarks. Then Q-Cuber bound state alpha S extractions would be much more precise. Is this a correct statement?
Of course,
or?
if you have a perfect quark mass, probably alpha S would come out much better. But that's not the case, right? I mean, you have to think that quarkonium masses have essentially zero error experimental. So all the problems that you have are from either perturbation theory or from some other parameter, which is not very precise like the bottom mass. I would rather use a strategy similar to what I presented on the bottomonium masses. That would be the next step, I think.
Can you please, and Diogo, also elaborate on this section, because we only have you, I think we have a few experts on quarkonia in this workshop, so maybe if you can write down all these things in the white paper, that would be helpful.
Sure. I mean, I would not claim that I myself is an expert on. I'm an expert on quarkonium, but sure, we can write something.
Good. Anybody else wants to comment on this category or on the PDF?
Yes, we have wait a second. We have a hand.
Sorry.
Yeah,
sorry.
Yes, a very fast question. Sorry. Since you mix experimental and lattice data, do you know how much weight in your final result each of these two things? So what constrain more your final result of alpha? Is the lattice data or the experimental ones?
I think it was the experimental one, but you see, I mean, I don't remember because this was done like 2 years ago. Maybe Diogo has better memory, but if you look into the central values, right? The central value of the only real data is very close to the central value of the combined. So that's what I don't know, pushes me to saying that probably the experimental data has a little bit more impact.
Can I make a short comment?
Sure.
No, I just wanted to say that what is our final value may not necessarily include the lattice data, because if we mix the experimental data with the lattice data, we're going to have some sort of a hybrid alpha S determination. So we can also consider our value from the Charmonium Sum Rules as our final value, I would say.
Yeah.
Yeah, there's actually a small sort of general comment here, which is that if PDG just takes the lattice value from the flag report, but there are going to be these hybrid determinations that use both experimental and so this needs to be kind of rethought, right? Because otherwise you get a funny way of counting contributions. So this is not a comment on Diogo's and Vicent's work, but just and so now it has not contributed to either PDG or a flag yet because it doesn't pass flag criteria. But you know, this is going to happen in the future, right? So something to consider.
Yeah. So the lattice also contain data, of course.
Yeah.
Otherwise, you can't determine the parameters. But I agree, it will be requiring some thinking when in the future more determinations arise where you get some information from lattice and data inside and from other ways.
It's the same issue we have with the electroweak fit of alpha S, right?
What do you mean, Julia?
That also contains data that are a lot of our. We have this electroweak fit.
Yeah,
but it's driven by the Z seed observables mostly.
Right.
So.
Sure, but still, there is some overlap.
Yeah, there is some overlap, and the counting will be extremely difficult, but it will be even more difficult if it concerns the most precise determinations which come from lattice.
Yes, absolutely. So wait a second.
so far, I think the experimental data used on the lattice are completely orthogonal to the data that's being used here, right? I mean, like what the work that Alberto talked about, they basically use the photon mass to set the scale, and that's it, right? I mean, so it's a low scale hadronic quantity, so it is not yet related, but this is going to change, you know, when lattice gets good at measuring 2-point functions, and, you know, I mean, and like what Diogo and Vicent are looking at, then it's going to be mixed.
Right.
Also maybe from flag, it would not be very difficult to get some kind of correlation. So how much each method weights in the final value of the flag average. So for example, for this particular case, I think that you can safely consider the lattice average and the result of Van Zandt uncorrelated, but it would be a very small error. But currently you can, yeah. Okay, if it doesn't pass the flag criteria, it doesn't enter. But I mean, even from flag, you could get this, even by reading the review. So that can be solved in some sense.
So I don't know, it's 7:10. Maybe we should now stop the discussion today.